Hello there, and welcome to Science for Sleep, a place where curiosity is allowed to slow down, where questions are never urgent, and where science doesn't rush to conclusions or demand wide-open eyes. This is a space for winding thoughts to loosen, for ideas to stretch out comfortably, and for the mind to explore without needing to arrive anywhere in particular. Whether you're listening at the end of a long day, in the early quiet of morning, or somewhere in between, you're very welcome here. Tonight, or today, or whenever this moment happens to find you, we're going to spend some time with a question that sounds simple at first, almost casual, but becomes much larger the longer you sit with it. It's a question that doesn't ask for quick answers or sharp definitions. Instead, it invites patience. It asks us to look outward, and then, gently, to notice how small our view really is. The question is this: how much of the universe have we actually observed? At first glance, it might feel like the answer should be reassuring. After all, we have powerful telescopes, detailed maps of distant galaxies, images of nebulae that look like glowing clouds of colour suspended in darkness. We can name stars by the billions, measure cosmic radiation, track planets orbiting suns far beyond our own. We send probes into deep space, land machines on other worlds, and receive signals from objects so far away that their light began its journey long before humans ever looked up in wonder. It feels as though we've seen quite a lot. And yet, when scientists pause and look at the numbers carefully, when they examine what is directly observed versus what is inferred, calculated or guessed at with careful mathematics, a different picture begins to form. One that is less complete, less confident, and strangely more fascinating. It turns out that almost everything we know about the universe sits atop a much larger foundation of what we haven't seen, haven't touched, and haven't directly measured. This isn't a failure of science. It's not a mistake or a missing piece that simply needs a stronger telescope or a bigger budget. It's a consequence of where we are, how the universe behaves, and the limits placed on us by distance, time, and the speed at which information can travel. Even with all our technology and cleverness, we're still standing in one small location, looking out through a narrow window, trying to understand something unimaginably vast. Before we drift too far into that immensity, let me ask you something simple. Where are you listening from right now? Are you in a familiar room, a place you return to every night, or somewhere slightly unusual? Is it late with the world quiet around you, or is there still movement and noise beyond the walls? And what time is it where you are? Not in a philosophical sense, just the ordinary human one. Evening, early morning, or a moment stolen between responsibilities. It's interesting to think that while you're here, listening to this, the universe outside is doing what it always does, expanding, shifting, moving forward, completely unconcerned with our clocks. If you find this kind of slow exploration calming or quietly intriguing, you're always welcome to support this space by liking the video or subscribing. It helps keep this corner of thoughtful calm available for others who might need it. There's no rush though. Nothing here requires urgency. Now let's ease back into the question at hand. When we say the universe, we're not talking about a single object or a defined place. We're talking about everything that exists, all space, all time, all matter, all energy. Every galaxy, every star, every particle, every empty stretch where nothing much seems to be happening. It's a word that tries to hold everything at once, which already makes it a little slippery. And when we talk about observing the universe, we usually mean something quite specific. We mean detecting it in some measurable way, seeing light with our eyes, or with instruments designed to catch wavelengths we can't naturally perceive. Measuring radiation, recording motion, tracking gravitational effects. Observation, in science, is tied to evidence that can be recorded, shared, and tested. It's not the same as imagining or speculating, even when speculation is informed and careful. This distinction matters, because much of what we know about the universe does not come from direct observation in the everyday sense. We don't see most things the way we see the moon or the sun or a photograph of a distant galaxy. Instead, we detect subtle effects. We measure influences. We infer the presence of things based on how other things behave. And inference, no matter how well supported, is not the same as observation. One of the most important limits on what we can observe comes from something very ordinary and very strict. Light takes time to travel. No signal, no matter how energetic, can move faster than light. That means when we look out into space, we're also looking back in time. The farther away an object is, the older the light we're receiving from it. When astronomers observe a galaxy 1 billion light years away, they're not seeing it as it is now. They're seeing it as it was 1 billion years ago. This alone places a boundary around what we can observe. The universe has a finite age, about 13.8 billion years as far as current measurements can tell. That means there is a maximum distance from which light has had time to reach us. Beyond that distance, the universe may continue, but its light simply hasn't arrived yet. Not because it doesn't exist, but because time hasn't allowed the message to get here. This leads to the idea of the observable universe. It's not the entire universe. It's the portion of the universe from which light has reached us since the beginning of cosmic expansion. It's a bubble centered on our location, not because we're special, but because observation always happens from somewhere. Every observer, anywhere in the universe, would have their own observable region, centered on themselves. Even within that observable region, what we can actually detect is limited further. Space is not empty in a helpful way. Light can be absorbed, scattered, stretched, and weakened. Dust clouds block visible light. Gas distorts signals. Expansion stretches wavelengths until they fade into forms that are difficult to detect. Some regions are simply too faint, too diffuse, or too distant for our instruments to pick up clearly. And then there's the uncomfortable realization that the matter we can directly observe makes up only a small fraction of what seems to exist. Stars, planets, gas, dust, everything that emits or reflects light, all of it combined accounts for a surprisingly small slice of the universe's total content. Most of what influences cosmic behavior appears to be invisible, interacting through gravity rather than light. This means that when we look at the universe and say, "This is what's out there," we're really saying, "This is what we can currently detect using light and a few other indirect signals." The rest remains unseen, not because it's hidden on purpose, but because the universe doesn't make everything easy to observe. It's worth pausing here to notice how strange this is from a human perspective. We evolved to navigate a world where seeing usually means knowing. If you can see a predator, you can avoid it. If you can see food, you can gather it. Vision became a primary way of understanding reality. Even today, phrases like "I see" are used to mean "I understand." But the universe doesn't work on those terms. It doesn't present itself in a way that matches human intuition. Much of it doesn't glow. Much of it doesn't interact with light at all. Some of it only reveals itself through mathematical footprints, subtle distortions, or effects that become noticeable only when examined on enormous scales. So when we ask how much of the universe we've actually observed, we're not just asking a question about distance or technology. We're asking something deeper. We're asking how much of reality is accessible to beings like us, standing on a small planet using tools built from the same matter we're trying to understand. This question also invites a quieter kind of humility. Not the dramatic kind that makes us feel insignificant, but a calmer one that reminds us that knowledge is always partial, that understanding grows but never finishes, that the universe doesn't owe us clarity or completeness. And yet, despite these limits, what we have observed is still remarkable. The fact that we can say anything at all about galaxies billions of light years away is extraordinary. The fact that we can trace the history of the universe back to a hot, dense beginning using faint background radiation is something no previous generation could have imagined. Even our partial view is deep and detailed in ways that would have seemed impossible not long ago. Still, partial is partial. And recognizing that doesn't diminish what we know. It places it in context. It reminds us that discovery is an ongoing process, not a finished collection. That every observation opens up new questions rather than closing the book. It's enough to rest with the idea that our view of the universe, impressive as it is, represents only a small portion of what likely exists. Not because we've failed to look hard enough, but because the universe is vast in ways that resist being fully seen. And as we continue, we can begin to explore what that unseen majority might mean, not just for science, but for the way we think about our place within it. Before telescopes, before equations, before ideas about galaxies and cosmic expansion, there is a much simpler image that has always been with us. A person standing on solid ground, lifting their eyes toward the sky. No instruments, no data, just the quiet awareness that whatever is overhead is vast, distant, and mostly unreachable. This is where our relationship with the universe begins, not in laboratories or observatories, but on a small piece of rock under an open sky. The Earth, when described plainly, is not an impressive object by cosmic standards. It is a rocky sphere orbiting an average star in the outer regions of an ordinary spiral galaxy. It has no special position, no central role, no obvious markers that would draw attention from across the cosmos. And yet, it is the only place we know of where the universe has become aware of itself, at least in the limited human sense of the phrase. Every question we ask about the universe, every observation we make, every image we collect, begins here. This matters more than it might seem. All observation is shaped by perspective, and our perspective is fixed to this planet. We are not hovering above the universe. We are not spread evenly throughout it. We are located at a specific point, moving at a specific speed, embedded in a specific gravitational environment, surrounded by a particular mix of matter and radiation. There is no neutral vantage point from which the universe can be observed as it truly is. There is only observation from somewhere, and that somewhere is always here. When you look up at the night sky with the unaided eye, what you see feels expansive. Thousands of stars scattered across darkness, patterns traced by human imagination, faint smudges that hint at something beyond individual points of light. For most of human history, this view was the universe. Everything beyond the Earth was assumed to be arranged on, or just beyond a celestial sphere, close enough to be part of a single structure. Even now, with modern understanding, the emotional impression hasn't entirely changed. The sky still feels large. It still creates a sense of openness, of distance, of something overhead that is bigger than daily concerns. But intellectually, we know that this familiar sky represents an extremely shallow slice of reality. Almost everything visible to the naked eye exists within our own galaxy, and even then, it's only a tiny fraction of what the galaxy contains. The Milky Way itself is vast beyond ordinary comprehension. It contains hundreds of billions of stars, along with planets, gas clouds, dust lanes, and objects that emit no light at all. And yet, when you stand outside on a clear night, far from city lights, what you see is mostly the nearby neighbourhood. The stars that appear brightest are often among the closest. Distance dims light quickly, and the universe does not provide many convenient beacons. This creates an illusion that has shaped human intuition for a long time. Brightness feels like importance. Proximity feels like dominance. The things we see most clearly feel like the main content of reality. But in space, visibility has very little to do with abundance or significance. Some of the most influential structures in the universe are invisible to our eyes. Some of the brightest objects are relatively rare. What stands out is not always what matters most. Standing on Earth also means standing within an atmosphere, a protective layer that both enables life and limits observation. The atmosphere filters radiation, blocks certain wavelengths entirely and distorts others. This is fortunate for biology and inconvenient for astronomy. Many forms of light never reach the ground. Ultraviolet radiation, X-rays, gamma rays, and much of the infrared spectrum are absorbed before they can be detected by ground-based instruments. This is why so much modern astronomy takes place above the atmosphere, using satellites and space telescopes. Even then, observation remains partial. Each instrument is tuned to a narrow slice of the electromagnetic spectrum. Each detector sees only what it is designed to see. No single telescope captures the universe in full. Instead, astronomers assemble a patchwork, combining data from different instruments, different wavelengths, and different methods, hoping that the composite picture is closer to reality than any single view. Still, all of this happens from roughly the same location. Whether a telescope is on a mountaintop or in orbit, it is still bound to Earth, moving with the planet around the Sun, with the Sun around the galaxy, with the galaxy drifting through space. We cannot step outside this motion. We cannot stop the universe to take a clearer look. Everything we observe is shaped by our movement through space and time. There is also a more subtle limitation that comes from scale. Human senses evolved to operate within a narrow range of sizes, speeds, and energies. We are comfortable with objects that fit in our hands, distances we can walk, and time spans we can remember. The universe operates on scales far outside these ranges. Distances stretch for billions of light years. Objects weigh more than entire solar systems. Events unfold over millions or billions of years. Because of this, even when we collect accurate data, our intuitions struggle to keep up. Numbers lose meaning. Comparisons become abstract. We talk about galaxies colliding, but the word collision does not carry the same implications in space as it does in everyday life. Stars pass through one another without touching. Timescales stretch so far that cause and effect blur together. Standing on a small rock means standing with a brain that was never designed to comprehend such extremes. We rely on mathematics, models, and metaphors to bridge the gap. These tools are powerful, but they are also translations. They convert cosmic behavior into forms we can handle. In doing so, they inevitably simplify and omit. This is another reason why observation is not the same as understanding. We can detect a light from a distant galaxy, measure its redshift, estimate its mass, and infer its motion. But this does not mean we grasp what it is like to exist there, or how it fits into the universe as a whole. Observation gives us data, not experience. It gives us outlines, not immersion. There is also the matter of time. The Earth has existed for about 4.5 billion years. Humans have existed for a tiny fraction of that span. Scientific observation, as we practice it now, has existed for only a few centuries. Modern cosmology, with its sophisticated instruments and theories, is younger still. This means that our observational record is extraordinarily brief compared to the age of the universe. We're attempting to understand a 13.8 billion-year-old universe using a snapshot that covers a few hundred years at most. We extrapolate backward and forward, using physical laws that appear consistent, but our direct observations occupy a vanishingly small temporal window. We are like someone trying to understand an entire novel by reading a single paragraph in the middle. This doesn't make the effort pointless, it makes it delicate. It means that conclusions must be provisional, open to revision as new data arrives. It also means that certainty is rare. Much of cosmology operates at the edge of what can be tested directly. Hypotheses are evaluated based on consistency, predictive power, and compatibility with existing observations, not on repeated direct measurement. Standing on Earth also means dealing with noise. Signals from the universe arrive weak and distorted. They are buried in background radiation, instrumental interference, and random fluctuations. Extracting meaningful information requires careful statistical analysis and long periods of observation. Even then, some signals remain ambiguous. Multiple explanations can fit the same data. This is not always obvious from the way discoveries are presented. Headlines often suggest clarity and resolution, a new image, a new measurement, a new theory. But beneath that presentation lies a process filled with uncertainty, debate, and gradual refinement. Observation is not a single act. It is an accumulation of evidence, always incomplete, always subject to reinterpretation. There is something quietly grounding about this. Standing on a small rock, looking up, reminds us that knowledge is not a conquest. It is a conversation between limited observers and an expansive reality. We do not dominate the universe by observing it. We listen carefully to the faint signals that reach us, and we do our best to make sense of them. It's also worth remembering that the Earth itself blocks half the sky at any given moment. From any location on the planet, only part of the universe is visible. The rest is hidden below the horizon. Over time, as the Earth rotates, different regions come into view, but even then, observation is fragmented. No single observer ever sees the entire sky at once. This fragmentation extends to human collaboration. Different observatories, located in different hemispheres, must share data to create a fuller picture. Knowledge of the universe is distributed, not centralized. It depends on cooperation across cultures, languages, and generations. No single mind holds it all. As we stand here, metaphorically speaking, on this small rock, it becomes clear that our observational limits are not just technical. They are fundamental. They arise from where we are, what we are made of, how we perceive, and how the universe behaves. Even with perfect instruments, some things would remain out of reach, simply because information takes time to travel, and because the universe itself has boundaries defined by its history. This realization does not shrink the universe. It expands our appreciation of it. Knowing that we see only a fraction does not make that fraction less meaningful. It makes it precious. Each photon that reaches us has travelled an immense distance. Each signal carries a story from a place we will never visit. Each observation is a small success against overwhelming scale, and as we continue to look outward, we begin to notice something else. The limits of observation are not uniform. Some boundaries are sharp, others are gradual. Some are imposed by physics, others by technology, and still others by interpretation. Understanding these limits helps us understand not just what we know, but how we know it. From here, it becomes natural to ask more specific questions. How far exactly can we see? What defines the edge of our observable region? What lies beyond it, if anything? And how do we even begin to talk about places that cannot, in principle, send us information yet? How far can we actually see from here? Not how far we imagine, not how far the universe might extend, but how far information has genuinely reached us in a form we can detect. When people hear about powerful telescopes, it's easy to assume that seeing farther is simply a matter of magnification, as if the universe were a landscape that becomes clearer the more you zoom in. In everyday life, that's often true. A pair of binoculars lets you see a distant hillside more clearly. A microscope reveals structures invisible to the naked eye. It feels intuitive to imagine telescopes working the same way, only on a much larger scale. But astronomy does not work like that. Distance in the universe is not overcome by making things bigger. It is constrained by time. Light does not arrive instantly. It moves quickly, but not infinitely so. Every second, light travels about 300,000 kilometers. That sounds fast until you compare it to the size of space. Light from the moon takes a little over a second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star system beyond the sun takes over 4 years. Already the numbers begin to stretch beyond ordinary experience. When we look at something far away, we're not seeing it as it is now. We're seeing it as it was when the light left it. This is not a philosophical statement. It is a physical one. Observation is delayed information. The farther we look, the further back in time we are forced to look as well. This means that the question, how far can we see, is inseparable from the question how far back in time can we observe, and that leads directly to a hard boundary. The universe has not existed forever. There was a beginning, not necessarily a single point in space, but a moment in time when the universe transitioned into the state we can meaningfully describe. Before that, our current theories stop working, and observation becomes undefined. The universe is about 13.8 billion years old. That means the oldest possible light we can receive today has been travelling for 13.8 billion years. Anything farther than that, even if it exists, has not had time to send information to us yet. There has simply not been enough time for light to cross the distance. This creates a horizon, not in space alone, but in space-time. It is not an edge you could travel to. It is a limit imposed by the finite age of the universe and the finite speed of light. Everything beyond that horizon is currently unobservable, not because it is hidden or blocked, but because causality has not connected it to us yet. Even within this horizon, distance is deceptive. The universe is expanding. Space itself is stretching. As a result, objects that emitted light billions of years ago are now much farther away than they were when that light began its journey. When astronomers say they are observing something 13 billion light-years away, they are describing the travel time of the light, not the current distance to the object. In fact, the most distant objects we can observe today are now more than 40 billion light-years away in terms of present-day distance. That number surprises many people, because it seems to contradict the age of the universe, but it doesn't. The universe expanded while the light was in transit. The light did not travel through static space. It travelled through space that was stretching as it went. This distinction matters because it shows that distance in the universe is not a fixed ruler laid out once and forever. It is dynamic. It changes over time. And our observations are always tied to the moment when the light was emitted, not to where the object happens to be now. Our eyes, unaided, are extremely limited. On a clear, dark night, the farthest individual stars you can see are a few thousand light-years away. Almost all of them are within our own galaxy. The Milky Way itself is about 100,000 light-years across. Everything visible without instruments fits comfortably inside that span. Telescopes extend that reach dramatically, but not infinitely. Each improvement in sensitivity allows astronomers to detect fainter objects. Faintness is often a sign of distance, but it can also indicate small size, low energy output, or obscuration by dust. Disentangling these factors is part of the challenge. The most distant things we can observe directly are not stars or planets, but radiation left over from the early universe itself. This radiation does not come from a specific object like a galaxy. It comes from a time when the universe became transparent to light, roughly 380,000 years after the beginning. Before that moment, the universe was too hot and dense for light to travel freely. Photons were constantly scattered by charged particles. Once the universe cooled enough for atoms to form, light could finally move through space without being immediately absorbed. That light has been travelling ever since. Today, it reaches us as a faint background glow detectable in microwave wavelengths. This radiation marks the farthest distance we can observe in any direction. It does not show us objects in the usual sense. It shows us conditions. It is a snapshot of the universe at a very early stage, stretched and cooled by expansion. In practical terms, this radiation defines the limit of what we can see. We cannot observe anything older than that moment using light, because there was no free light travelling before it. Even if structures existed in some form, their information cannot reach us through electromagnetic signals. This means that when we talk about seeing the edge of the universe, what we really mean is seeing the edge of our observational capacity. The universe itself does not end there. It simply stops being visible in a direct way. There are other ways of probing distance that do not rely solely on light. Gravitational waves, for example, carry information through distortions in space-time itself. Neutrinos can travel through matter almost unhindered. These messengers offer new ways to observe the universe, but they do not remove the fundamental horizon imposed by time. They too are limited by how long the universe has existed and how fast signals can propagate. Even within the observable region, distance affects clarity. As objects get farther away, details blur together. Individual stars become unresolved points. Galaxies shrink into smudges. Structures merge into statistical patterns rather than discrete forms. At great distances, we do not study individual objects. We study populations, distributions, and averages. This is another subtle limitation. Our picture of the distant universe is not a detailed portrait. It is more like a low-resolution map. We can identify trends and broad features, but fine structure is lost. We know that galaxies existed early on, but we do not see them the way we see nearby ones. We infer their properties from limited signals. Distance also means scarcity. The farther out we look, the fewer photons arrive. Light spreads out as it travels. By the time it reaches us from the early universe, it is extremely weak. Detecting it requires long observation times, sensitive instruments, and careful data processing. Noise becomes a serious problem. Random fluctuations can masquerade as signals. Confidence requires repetition and independent confirmation. Because of this, our vision of the farthest universe is statistical rather than personal. We do not point to a single distant point and say, with certainty, this is exactly what is there. Instead we say, given the data we have, the most likely explanation is this. Observation becomes an exercise in probability. It's also important to remember that seeing farther does not necessarily mean seeing more variety. The early universe was simpler than the one we inhabit now. Structures had not yet fully formed. Matter was more evenly distributed. Diversity emerged over time as gravity amplified small differences. When we look far away, we are looking at a universe that had not yet developed the complexity we're familiar with. This means that our deepest observations do not show us exotic, unfamiliar landscapes. They show us uniformity, slight variations, and the seeds of later structure. Paradoxically, the farther we see, the less detailed the universe appears. All of this reshapes the original question: how far can our eyes actually see? The answer is not a single number. It depends on what we mean by seeing, what signals we use, and how we interpret them. Our naked eyes see a small region of a single galaxy. Our instruments see billions of galaxies, but only in certain wavelengths and only back to a certain time. Beyond that, the universe continues, but not in a way that sends us light. This does not mean that everything beyond the horizon is unknowable forever. It means that knowledge will come, if at all, through indirect reasoning, through models, consistency checks, and theoretical constraints. We will not receive images or signals from those regions anytime soon. They are not part of our observable story yet. There is something quietly grounding about that. It reminds us that observation is not limitless, that knowledge grows within boundaries, that even the most advanced instruments operate under rules that cannot be bypassed. Once the idea of distance is tied firmly to time, another concept begins to take shape almost on its own. It's not a boundary you can point to on a map, and it's not an edge you could ever approach, but it defines everything we can possibly observe. This is the region often described as the observable universe, and thinking of it as a kind of bubble is one of the least misleading ways to picture it. Imagine standing exactly where you are now, wherever that happens to be, and drawing an invisible sphere around yourself. That sphere expands outward in every direction, not through space in the usual sense, but through space-time. Its size is determined by how far light has been able to travel since the universe became transparent and signals could move freely. Everything inside that sphere has had enough time to affect you in some way. Everything outside it has not yet. This bubble is not centered on Earth because Earth is special. It is centered on Earth because observation always has a center. If you were standing on a planet in a galaxy 10 billion light-years away, your observable universe would be centered there instead. It would contain many of the same large-scale features, but not exactly the same objects. Some regions you can observe would be invisible to them, and some regions they could observe would be invisible to you. That realization alone changes the way the universe feels. There is no single observable universe. There are countless overlapping observable regions, one for every possible observer, each limited by time and the speed of light. What we casually call the observable universe is really just ours. The size of this bubble is often misunderstood. Because the universe is about 13.8 billion years old, it seems natural to assume that the observable universe has a radius of about 13.8 billion light-years. But expansion complicates that picture. Space itself has been stretching the entire time light has been travelling. The result is that the most distant regions we can observe today are much farther away now than when the light left them. When astronomers calculate the current size of the observable universe, they arrive at a radius of roughly 46 billion light-years. That means the full diameter is about 92 billion light-years across. This is not because light travelled faster than expected. It's because the space between points expanded while the light was in transit. This bubble is not static. It grows over time. As the universe ages, light from slightly more distant regions has time to reach us. The observable universe slowly expands, not because space is expanding faster within it, but because the horizon of what has had time to connect with us moves outward. At the same time, there is a subtle counteracting effect. Due to the accelerated expansion of the universe, driven by whatever is causing space to stretch faster over time, some regions that are currently observable will eventually become unobservable in the future. Light emitted from them now may never reach us. They are already receding faster than the signals they send can cross the expanding space. This means the observable universe is not just a growing bubble. It is a bubble with a complicated future. Some regions are entering it. Others are effectively slipping away, becoming forever disconnected. Observation is not simply cumulative, it is shaped by the dynamics of expansion. Inside this bubble, everything we know directly about the universe resides. Every galaxy image, every measurement of cosmic radiation, every detected gravitational wave. Outside, it lies a vast region that may be similar, or wildly different, or structured in ways we have not imagined. But whatever lies there is currently beyond direct observation. It's important to be precise here. Beyond observation does not mean beyond existence. The universe does not stop at the edge of the observable bubble. There is no physical wall, no sudden drop-off. The boundary exists only from our perspective, defined by what information has reached us so far. This distinction often gets lost in casual discussions. People talk about the observable universe as if it were the whole universe, simply because it's the part we can talk about with evidence. But cosmological models strongly suggest that the universe extends far beyond what we can observe, possibly infinitely far. The observable bubble may be just a small patch of a much larger whole. Within our bubble, matter is distributed in a way that appears broadly uniform on very large scales. Galaxies cluster into filaments and walls, separated by vast voids, forming a structure sometimes described as cosmic web-like. But when averaged over enormous distances, the universe looks roughly the same in every direction. This uniformity supports the idea that regions beyond our horizon are likely similar in large-scale structure, though we cannot confirm that directly. The bubble also has a temporal dimension. When we look at distant objects near the edge of the observable universe, we're seeing them as they were very early in cosmic history. As we look closer to home, we see later stages of evolution. The observable universe is not just a map of space, it is a layered record of time. This layering creates a strange effect. Nearby regions show mature galaxies, heavy elements, complex structures. Farther regions show younger galaxies, simpler compositions, and earlier stages of formation. At the farthest limit, we see not objects, but conditions, a nearly uniform glow marking the moment when light first travelled freely. So within this bubble, distance corresponds to age. Space becomes a timeline. Observation becomes archaeology on a cosmic scale, where the deepest layers are the oldest. And yet, despite this richness, the bubble contains far less than we might assume. Even within the observable universe, only a small fraction of what exists can be seen directly. Most matter does not emit light. Most energy does not interact with photons in a detectable way. Even inside the bubble, observation is incomplete. The idea of the bubble also highlights something subtle about our role as observers. We often imagine ourselves as looking out into the universe, as if the universe were arranged around us for viewing. In reality, the observable universe is defined by our past-like cone, a region shaped by the intersection of our world line with the flow of space-time. It is not a window we open. It is a region carved out by physics. Nothing about this bubble is adjustable. We cannot make it larger by trying harder. We cannot peek beyond it by building a better telescope. We can refine what we see within it, sharpen details, detect fainter signals, but the boundary itself is not something technology can push past. This places an interesting constraint on knowledge. There are questions we can meaningfully ask and test using observations. There are also questions that may forever remain speculative, not because they are meaningless, but because the universe does not allow information about them to reach us. For example, we can ask whether the universe is infinite or finite in extent. We can build models that favour one possibility over another, but we cannot observe the entire universe to check. The answer may always remain inferred rather than confirmed. Similarly, we can ask whether the laws of physics are the same everywhere. Observations within the bubble suggest consistency, but beyond it, we cannot verify. We assume uniformity because it fits the data we have, and because alternative assumptions introduce unnecessary complexity. But assumption is not observation. The bubble also shapes how we think about cosmic history. When we describe events in the early universe, we are describing events that occurred everywhere, not just here. But our evidence comes from a shell of radiation surrounding us, arriving from all directions at once. We reconstruct a global story from a local signal. This is one of the quiet triumphs of cosmology. Using limited information from within a bubble, scientists have pieced together a coherent narrative of cosmic evolution. But it's also a reminder that the narrative is constrained by perspective. Another consequence of the observable bubble is that it limits causal influence. Regions outside it have not affected us yet. Their gravitational influence has not reached us. Their light has not arrived. They are for now causally disconnected. This does not mean they never will be, but under current models of accelerated expansion, many of them will remain forever out of reach. That idea can feel unsettling at first. It suggests that vast regions of reality exist that will never matter to us in any practical sense. They will never influence our history or our future, but it can also be seen as a neutral fact. The universe is not obligated to be fully connected from every perspective. From within the bubble, we can still ask meaningful questions. How did structure form? Why does the universe have the properties it does? What governs expansion? These questions are answerable, at least in part, using the information available to us. The bubble does not trap curiosity, it frames it. Another distinction becomes important. Observability is not the same as emptiness. When we say there are regions beyond the observable universe, we're not saying there is nothing there. We're saying that whatever is there has not yet communicated with us. Even within the observable universe, large portions appear dark. Not empty, just non-luminous. This darkness is not confined to the horizon, it is everywhere. By the time the idea of an observable bubble is settled in, light starts to feel less like a simple messenger and more like a constraint. It's the fastest thing we know of, the ultimate speed limit of the universe, and yet it is also the reason we're always late to everything we observe. Every glimpse of the cosmos arrives with a built-in delay, and that delay quietly shapes every conclusion we draw. It's tempting to think of light as instantaneous because on human scales, it almost is. Turn on a lamp and the room fills with illumination so quickly that your brain doesn't register any waiting. Look at the sun and it feels present, immediate, right there in the sky. But even that familiar light is already 8 minutes old by the time it reaches your eyes. If the sun were to suddenly vanish, which it won't, we would continue to see it shining peacefully for 8 more minutes, completely unaware of what had happened. That small example contains the entire problem in miniature. Light always shows us the past. There is no such thing as seeing something now at a distance. The farther away an object is, the deeper into its history we are forced to look. Observation is never synchronized with reality at large scales. It is staggered, layered, delayed. As distance increases, this delay becomes impossible to ignore. Light from the nearest stars arrives years after it was emitted. Light from distant galaxies arrives millions or billions of years late. When astronomers observe a galaxy whose light has been travelling for 10 billion years, they are not seeing a distant version of the present universe. They are seeing a much younger universe, one that existed long before the Earth formed, before the Sun ignited, before the Milky Way reached its current shape. This creates a strange asymmetry in our knowledge. We know the nearby universe in detail. We can resolve individual stars, measure motions precisely, and track changes over time. As we look farther away, detail fades and certainty thins. The universe does not become more mysterious because it is stranger out there. It becomes more mysterious because we are seeing it earlier, with fewer photons, less information, and no way to revisit the scene. Light does not just carry images, it carries energy, timing, and context. But it also loses information as it travels. It spreads out, weakens, and gets stretched by the expansion of space. This stretching, known as redshifting, moves light toward the longer wavelengths. Light emitted as visible radiation may arrive as infrared or microwave radiation by the time it reaches us from the distant universe. This stretching does not erase information entirely, but it changes how that information must be interpreted. Instruments must be tuned to detect signals that no human eye could ever see. Entire observatories exist solely to capture wavelengths that never reach the ground, blocked by the atmosphere or shifted beyond visible light. Even when light does arrive, it rarely travels in a straight, uninterrupted line. Along the way, it can be absorbed by dust, scattered by gas, or bent by gravity. Massive objects warp space-time, causing light to follow curved paths. This effect can magnify distant objects, distort them into arcs, or create multiple images of the same source arriving at different times. These distortions are useful. They allow astronomers to detect mass that emits no light, but they also complicate interpretation. What looks like one object may be many. What looks bright may be magnified. What looks dim may be distant or merely obscured. Distance and delay become tangled together, and disentangling them requires careful modelling. Another quiet complication is that light does not carry labels. When a photon reaches a detector, it does not announce where it came from or how long it travelled. That information must be reconstructed from context. Astronomers infer distance by measuring redshift, brightness, spectral features, and by comparing objects to known reference points. Each method carries assumptions, each introduces uncertainty. Because of this, cosmic distance measurement is not a simple ruler laid across space. It is a ladder built from many overlapping techniques, each reliable over a certain range, each calibrated against the others. Errors compound as distance increases. Confidence decreases as delay grows. This matters because delay does more than blur images. It freezes events in mid-process. When we observe distant galaxies forming stars, we are watching processes that may have ended billions of years ago. When we detect a supernova far away, the explosion has already faded into history by the time the light reaches us. We cannot intervene, revisit, or confirm outcomes in real time. The universe does not offer replays. It sends one stream of information, and we receive it when it arrives, ready or not. This one-way flow creates an illusion of simultaneity that does not actually exist. When we look at the night sky, all the stars appear to exist together, arranged in a single moment. In reality, each point of a light represents a different slice of time. Some photons left their sources thousands of years ago. Others began their journey before human civilization existed. Still others started travelling before Earth itself was formed. The sky is not a snapshot. It is a collage assembled from different eras, layered so smoothly that the seams are invisible. This has consequences for how we think about cosmic evolution. We often speak as if the universe has a single age at any given moment, but age depends on where you look. Nearby regions are older in terms of observed development. Distant regions are younger. The universe does not present itself as a uniform present. It presents itself as a gradient of pasts. This is why astronomers can study cosmic history without travelling through time. By looking farther away, they automatically look earlier. Distance becomes a proxy for age. But this only works because of delay. Without the finite speed of light, the universe would collapse into a single instant from our perspective, and history would be inaccessible. Delay, then, is not just a limitation, it is also an opportunity. It allows us to see stages of development that no longer exist nearby. It lets us observe the universe when it was simpler, denser, and more uniform. It gives us evidence for how structure formed and evolved. At the same time, delay ensures that there will always be gaps. There are events we will never see because their light will never reach us. There are regions whose future we can infer but never observe. There are changes happening right now in distant galaxies that will not be known to us for billions of years, if ever. Cosmic delay also means that the universe we describe is always outdated. Every model is based on information that arrived late. This does not make the models wrong, but it does mean they are reconstructions, not live feeds. The universe we talk about is a memory, not a current broadcast. This becomes especially important when thinking about expansion. As space stretches, some regions recede faster than light can bridge the gap. Light emitted from those regions today will never reach us. The delay grows without bound. Those parts of the universe effectively drop out of observational history. This introduces a kind of cosmic asymmetry. The observable universe grows as time passes, but the set of regions we can ever observe may shrink in practical terms. There are galaxies we see now whose future light will never reach us. We see them only because their past light escaped before expansion accelerated too much. This makes observation an exercise in timing as much as distance. Some information arrives just in time, some arrives too late, some will never arrive at all. Another subtle effect of delay is that it limits feedback. In everyday life, observation and response are closely linked. You see something happen and react almost immediately. On cosmic scales, reaction is impossible. By the time you see an event, it is long over. There is no interaction, no response loop. Observation is passive. This passivity shapes the kind of science we can do. Astronomy is observational, not experimental in the usual sense. We cannot change conditions and see what happens. We cannot repeat cosmic events. We can only observe what arrives and compare it to models. This makes interpretation central. Data does not speak for itself. It must be placed into a framework that accounts for delay, distance, distortion, and uncertainty. Competing models can often explain the same observations, especially when data is sparse or noisy. Despite this, the consistency of observations across vast distances is remarkable. Light arriving from different regions and different times tells a coherent story. The same physical laws appear to operate everywhere we can see. The same patterns emerge again and again. This coherence is one of the strongest reasons scientists trust their models of cosmic history. Still, trust does not equal completeness. Light tells us only what it can. It interacts with charged particles and fields. It does not interact directly with everything. If something does not emit, absorb, or scatter light, it remains invisible to electromagnetic observation. This brings us to a quiet but crucial realization. Even within the observable universe, even within the bubble defined by light's reach, there may be vast amounts of content that light simply does not reveal. Distance and delay limit how far we can see, but they also distract us from another limitation that operates much closer to home. Because the universe is not just limited by how far signals can travel, it is also limited by what kinds of signals exist at all. When people picture space, darkness is usually the first thing that comes to mind, an endless black backdrop scattered with points of light. It feels intuitive to associate darkness with emptiness, as if the universe were mostly nothing, punctuated by a few bright objects. But that intuition turns out to be misleading. Darkness in space does not mean absence. It rarely means nothing is there. More often it means something is present that does not announce itself with light. From where we stand, darkness feels passive. A room is dark when the lights are off. The assumption is that if you can't see something, it either isn't there or doesn't matter. On Earth, this usually works well enough. Our environment is dense with matter, and most objects interact with light in obvious ways. In space, however, light is a poor guide to abundance. The things that shine are not representative of everything that exists. They are simply the things that happen to glow. Stars dominate our visual understanding of the universe because they emit enormous amounts of light. They are energetic, hot, and easy to detect across great distances. Galaxies stand out because they contain billions of stars packed together. Nebulae glow when energized by nearby radiation. All of this gives the impression that light traces structure. But in reality, light traces only a particular kind of structure, one that is active, heated, or undergoing specific physical processes. Between the stars, between the galaxies, and even within them, there is far more material than light would suggest. Gas clouds too cold to glow, dust that absorbs light rather than emitting it, and matter that interacts only weakly with radiation, all contribute to the universe's content while remaining visually silent. Even the emptiest-looking regions of space are not empty in the everyday sense. They contain particles, fields, radiation, and structure on scales that are difficult to detect directly. A region that appears completely black to a telescope may still exert gravitational influence, bend light passing through it, and shape the motion of visible matter nearby. This is one of the first places where intuition breaks down. We're used to equating brightness with importance. In the universe, brightness often signals rarity. Stars are not the dominant form of matter. They are one outcome of matter, clumping under gravity and igniting nuclear fusion. Most matter never reaches that state. The darkness between stars within a galaxy contains gas that may one day form new stars, or may never do so. It contains dust grains that absorb starlight and re-radiate it at wavelengths we don't see with our eyes. It contains magnetic fields and cosmic rays. It contains structure, motion, and history, even when it looks like a blank space. On larger scales, the darkness between galaxies is even more deceptive. Galaxies are not isolated islands floating in nothingness. They are connected by extended structures of matter that stretch across millions of light years. These structures do not glow brightly, but they guide the formation and movement of galaxies. Without them, the universe would look very different from what we observe. Darkness also hides age. Some regions are dark not because they are empty, but because they are old. Stars burn through their fuel and fade. Galaxies can exhaust their ability to form new stars. Once energetic processes slow down, light output drops. What remains may still be massive and influential, but it no longer announces itself visually. There is also the issue of wavelength. Human eyes see only a narrow slice of the electromagnetic spectrum. When something does not emit light in that range, it appears dark to us, even if it is glowing strongly in other wavelengths. A cloud of cold gas may shine in radio waves, Warm dust may glow in infrared. High-energy processes may emit X-rays or gamma rays. Darkness in visible light often simply means the light is coming in a form we are not naturally equipped to see. Modern astronomy relies heavily on this realization. Many of the most important observations are made outside the visible spectrum. Telescopes tuned to radio, infrared, ultraviolet, and X-ray wavelengths reveal structures that optical telescopes miss entirely. What appears as a void in visible light can become crowded and active when viewed differently. Still, even when all wavelengths are considered, there remains a deeper darkness that does not go away. This darkness does not glow at any wavelength. It does not emit, absorb, or scatter light in detectable ways. And yet, its presence is undeniable because of what it does. This is where darkness stops being a descriptive term and becomes a physical clue. Something unseen is shaping the universe on large scales. Galaxies rotate faster than they should, if only visible matter were present. Clusters of galaxies hold together more tightly than light alone can explain. Light from distant objects bends around invisible structures. The universe behaves as if there is far more matter than we can see. This unseen component does not hide in distant corners only. It is everywhere. It threads through galaxies, surrounds them, and outweighs their luminous content by a wide margin. It does not make itself visible through light, but it makes itself felt through gravity. Darkness in this context is not a lack, it is a signal. Understanding this changes the emotional texture of space. Darkness is no longer just an empty backdrop. It becomes active, structured, and essential. The universe is not a sparse scattering of glowing objects in a void. It is a complex arrangement where the brightest elements are carried along by a much larger invisible framework. There is also a psychological shift that happens here. Once you accept that most of what exists does not announce itself, you stop expecting completeness from vision alone. You begin to treat observation as indirect by default. Seeing becomes one input among many, not the final authority. This matters because so much of our language about the universe is visual. We talk about looking deeper, seeing farther, peering into space. These phrases suggest that the universe is something waiting to be revealed if only we stare hard enough. Darkness reminds us that revelation does not always come through sight. Some of the most important discoveries in cosmology came not from new images, but from noticing inconsistencies. Motions that didn't add up, patterns that didn't match expectations, effects without visible causes. Darkness drew attention to itself by refusing to behave like emptiness. Even the concept of a void is more complicated than it sounds. Cosmic voids are regions with fewer galaxies, but they are not empty. They contain matter, radiation, and structure at lower densities. They expand differently than denser regions. They play a role in the large-scale dynamics of the universe. Darkness, again, does not mean nothing is happening. On the largest scales, darkness dominates the universe's appearance. When astronomers map the distribution of matter, they find that luminous objects occupy a small fraction of space. Most of the volume of the universe is dark not because it is empty, but because it is diffuse and non-luminous. This has an interesting consequence. The universe we visualize, filled with galaxies and stars, is a biased picture. It highlights peaks in a much broader landscape. It shows us the mountaintops and ignores the valleys. To understand the full terrain, you have to account for what you cannot see. Darkness also carries information about limits. It marks the boundaries of what light can reveal. It shows where assumptions based on visibility fail. It forces scientists to develop new methods, new instruments, and new theories. In a way, darkness has been more productive than light. Light shows us what is obvious. Darkness shows us what is missing. And what is missing turns out to be most of the universe. Darkness is not just something between stars or at the edges of the observable universe. It is woven into the structure of everything we see. To understand how much of the universe we have actually observed, there comes a point where the question can no longer stay abstract. It stops being about distance or horizons or limits of vision and turns into something far more concrete. It becomes a question about missing weight, about motion that does not behave the way it should, about gravity that seems to come from nowhere. This is where the idea of dark matter enters, not as a speculative add-on, but as a response to observations that simply refuse to make sense otherwise. The story does not begin with a search for something invisible. It begins with very ordinary measurements. Astronomers watching stars orbit within galaxies noticed that those stars were moving far too fast. According to everything known about gravity, stars farther from the centre of a galaxy should orbit more slowly, just as planets farther from the Sun move more leisurely along their paths. The visible mass of a galaxy, its stars, gas and dust, should determine how fast things move. But when astronomers actually measured those speeds, the numbers didn't match. Stars at the edges of galaxies were racing along as if there were far more mass present than could be seen. If galaxies contained only the matter that emitted light, they should have flown apart long ago. Instead, they remained intact, held together by gravity from something unseen. At first, this discrepancy was treated with caution. Maybe the measurements were wrong. Maybe the distances were miscalculated. Maybe the laws of gravity behaved differently on galactic scales. But as observations improved and the same pattern appeared again and again, across different galaxies, in different regions of the universe, the conclusion became difficult to avoid. There was more matter than met the eye. This was not a small adjustment. The missing mass was not a minor correction. It outweighed visible matter by a large margin. In galaxy after galaxy, clusters of galaxies, and eventually in the large-scale structure of the universe itself, the same conclusion emerged. Most of the matter was invisible. This invisible matter did not behave like gas or dust. It did not clump into stars. It did not emit or absorb light. It passed through ordinary matter without obvious interaction, and yet it exerted gravity. It shaped orbits. It sculpted cosmic structure. It held galaxies together and guided their formation. Calling it dark was not a poetic choice. It was a practical one. Dark in this context simply means non-luminous. It does not glow. It does not reflect. It does not reveal itself through electromagnetic radiation. If you were to look directly at a region filled with dark matter, it would appear empty, and yet it would not be empty at all. This realization fundamentally altered the balance of the universe. Suddenly, everything that had been considered solid, familiar and visible became the minority. Stars, planets, gas clouds, nebulae, and even entire galaxies turned out to be surface features on a much larger invisible framework. The universe, it seemed, was built on scaffolding we could not see. What makes this especially relevant to the question of observation is that dark matter was not discovered by looking for it directly. It was inferred. Its existence was deduced from its effects. We observed motion, bending, clustering, and stability that could not be explained otherwise. Dark matter announced itself through absence, through the failure of visible matter to account for what was happening. This means that one of the most important components of the universe was never actually observed in the usual sense. No image of dark matter exists. No telescope has ever captured it directly. Every map of dark matter you may have seen is a reconstruction, built from gravitational effects and mathematical modelling, and yet its presence is woven into almost every observation of the large-scale universe. When galaxies form, they do so within halos of dark matter. When clusters of galaxies gather, dark matter dominates their mass. When light from distant objects bends and warps on its way to us, it does so because it passes through regions rich in unseen mass. One of the clearest demonstrations of this comes from observations of colliding galaxy clusters. In these events, clouds of hot gas collide and slow down, emitting X-rays as they interact. Galaxies themselves pass through mostly unaffected, like sparse swarms of bees passing through one another. But the majority of the mass, traced through gravitational lensing, moves with the galaxies rather than the gas. The result is a separation between where most of the light is and where most of the mass is. The gravitational influence is strongest where there is very little visible matter. This kind of observation makes it extremely difficult to explain the universe using only what we can see. Once dark matter is included, many puzzles resolve themselves. Galaxies remain stable. Large-scale structure forms in a way that matches observations. The cosmic web emerges naturally, with filaments of matter guiding the formation of galaxies over billions of years. But this resolution comes at a cost. It means accepting that most of the universe's matter is something fundamentally different from everything we are familiar with. Dark matter is not made of atoms. It does not form molecules. It does not interact with light in the way ordinary matter does. It is something else entirely. And here is where the question of observation becomes particularly sharp. We have built our understanding of reality around things that interact electromagnetically. Light has been our primary messenger. Chemistry, biology, and most of physics are grounded in interactions between charged particles. Dark matter sits outside that framework. This means that even though dark matter dominates the mass of the universe, it is largely inaccessible to our senses and to many of our instruments. We can detect it only indirectly, through gravity. We cannot pick it up, isolate it, or examine it in a laboratory in the usual way. We infer its properties by watching how it shapes the behavior of things we can see. This puts dark matter in a unique category. It is both essential and elusive. It is everywhere and yet nowhere in particular. It influences everything without revealing itself directly. Estimates suggest that dark matter makes up about 27% of the universe's total energy content. Ordinary matter, everything made of atoms, accounts for only about 5%. That means that everything we have ever directly observed, every star, planet, person, and particle, detected through electromagnetic interaction, represents a tiny fraction of what exists. In other words, when we look out at the universe and describe what we see, we are describing the minority component. This realization forces a quiet shift in perspective. The universe is not mostly stars and galaxies with a bit of darkness sprinkled in between. It is mostly dark matter, with visible structures forming where conditions allow ordinary matter to collect and ignite. Even the formation of galaxies depends on this invisible majority. In the early universe, dark matter began to clump first, forming gravitational wells. Ordinary matter fell into those wells, heating up, cooling, and eventually forming stars and galaxies. Without dark matter, structure formation would have proceeded very differently, if at all. This means that every galaxy we observe is, in a sense, a tracer. It marks the presence of a much larger unseen structure. When we map galaxies across the universe, we are really mapping the peaks of a dark matter landscape. Despite its importance, dark matter remains unidentified at a fundamental level. Scientists have many hypotheses about what it might be. Some propose new kinds of particles that interact only weakly with ordinary matter. Others explore alternatives to gravity itself. Experiments deep underground, in space, and at particle accelerators search for traces of dark matter interactions. So far, none have been definitively confirmed. This uncertainty is not a weakness. It is a reflection of how far observation can take us and where it stops. We know dark matter exists because the universe behaves as if it does. We know roughly how it is distributed and how much there is. But we do not yet know what it is. This gap between knowing that something exists and understanding its nature is significant. It highlights the difference between observational necessity and explanatory completeness. Dark matter solves many observational problems, but it also opens new ones. From the perspective of how little of the universe we have observed, dark matter is a central example. It shows that even within the observable universe, Even well inside the bubble defined by light's reach, most of what exists does not reveal itself directly. We live embedded in a structure dominated by something we cannot see, touch, or fully describe. Our planet moves through a halo of dark matter. Our galaxy orbits within a massive dark matter envelope. The motions of galaxies around us are shaped by invisible mass. And yet, if dark matter did not exist, our observations would make no sense. The universe we see would not hold together. The very fact that galaxies exist in stable forms is evidence of this unseen component. There is something humbling about that. The universe does not align itself with our senses. It does not privilege what we can easily detect. It includes components that require inference, patience, and acceptance of uncertainty. Once the presence of dark matter is accepted, the universe already feels very different from the one suggested by simple observation. Most of its mass is invisible, detectable only through gravity, shaping everything we see without ever announcing itself directly. For a while, that seemed like enough of a revision. The universe was stranger than expected, but still understandable within a framework where gravity pulled things together and structure formed through attraction. Then another discovery arrived, one that did not merely add an unseen component, but overturned expectations about how the universe behaves on the largest possible scale. This discovery did not come from looking deeper into space in the usual sense. It came from noticing something unsettling about motion itself, not the motion of stars within galaxies, and not even the motion of galaxies within clusters, but the motion of the universe as a whole. When astronomers began to measure how fast distant galaxies were moving away from us, and how that motion changed over time, they found something that contradicted the most basic intuition about gravity. The expansion of the universe was not slowing down. That statement is easy to gloss over, but it carries enormous weight. If the universe began in a hot, dense state, and has been expanding ever since, then gravity, acting on all the matter within it, should gradually slow that expansion. The pull of every galaxy on every other galaxy should act like a cosmic brake. The expansion might continue forever or eventually reverse, but it should decelerate. That was the expectation. It fit neatly with everything known about gravity. It matched common sense, and it turned out to be wrong. Observations of distant exploding stars used as standard reference points for measuring cosmic distances showed that faraway galaxies were receding faster than expected. Not only that, but the rate of expansion appeared to be increasing over time. The universe was not merely expanding, it was accelerating. This was not a subtle effect. It was not something that could be explained away by measurement error or local variation. Independent teams using different methods arrived at the same conclusion. The farther away they looked, the more pronounced the effect became. The universe's expansion was speeding up. Gravity alone could not explain this behavior. Something was counteracting it. Something was acting not as an attractive force, but as a kind of cosmic push, stretching space itself and driving galaxies apart more rapidly as time went on. This something did not show up as matter. It did not clump into structures. It did not orbit, collide, or form halos. It did not reveal itself through light, gravity in the usual sense, or any familiar interaction. Its presence was inferred solely from the way space expands. This is what we now call dark energy. The name, like dark matter, is descriptive rather than explanatory. Dark means unseen. Energy is used because whatever this component is, it affects the dynamics of the universe, particularly its expansion. Beyond that, the name does very little work. It does not tell us what dark energy is, where it comes from, or why it behaves the way it does. What makes dark energy especially strange is not just that it is invisible, but that it appears to be uniform. Dark matter clusters. It gathers around galaxies and filaments. Dark energy does not. it seems to be spread evenly throughout space, exerting the same influence everywhere. This uniformity has profound consequences. As the universe expands, the amount of dark energy does not thin out in the same way matter does. When matter spreads out, its density decreases. When space expands, dark energy appears to remain constant per unit volume of space, or possibly even increase in effect. The more space there is, the more influence dark energy has. This creates a feedback loop. Expansion creates more space. More space increases the influence of dark energy. Increased influence accelerates expansion. Over time, this effect dominates the behavior of the universe. Current measurements suggest that dark energy accounts for roughly 68% of the universe's total energy content. Combined with dark matter, this means that about 95% of the universe consists of components that have never been directly observed. Everything familiar, everything atomic, everything that makes up stars, planets, and people exists within the remaining 5%. This is not a poetic exaggeration. It is the accounting that best fits the data we have. From the perspective of observation, this is staggering. We tend to think of science as progressively revealing what is out there, filling in blanks with images and measurements. Dark energy represents the opposite. It is a blank that grows larger the more carefully we observe. Unlike dark matter, which reveals itself through structure and motion on many scales, dark energy reveals itself only through the expansion of the universe as a whole. You cannot point to a galaxy and say, "There it is." You cannot map it the way you can map mass distributions. You can only infer its presence statistically by comparing how fast things are moving at different distances and times. This makes dark energy deeply impersonal. It does not participate in the local drama of galaxies forming or stars burning. It operates quietly in the background, shaping the long-term fate of everything without ever becoming a visible actor. It also challenges language. We speak of energy as something that does work, that can be converted, stored, or released. Dark energy does not fit comfortably into that picture. It does not seem to power machines or fuel reactions. It simply exists, influencing the geometry of space. Some theories associate dark energy with the energy of empty space itself. In quantum physics, even a perfect vacuum is not truly empty. It seethes with fluctuations, temporary particles appearing and disappearing. The energy associated with this vacuum could, in principle, drive cosmic expansion. But here too, observation runs into limits. The simplest calculations of vacuum energy predict values that are wildly different from what is observed. The discrepancy is not small, it is enormous. Reconciling theory with observation in this case remains one of the biggest unsolved problems in physics. Other ideas propose that dark energy is not a constant property of space, but a dynamic field that changes over time. If so, its influence might evolve, altering the future of cosmic expansion in ways we do not yet understand. Again, observation can constrain these ideas, but only within the limits imposed by distance and delay. What dark energy ultimately represents may remain unknown for a very long time. It might require new physics, new concepts, or entirely new ways of thinking about space and time. For now, it remains an inferred presence, accepted because without it, the universe we observe cannot be explained. This brings us back to the central theme. How little of the universe have we actually observed? With dark energy, the answer becomes uncomfortable. We have observed its effects, but not its nature. We know it exists because the universe behaves as if it does, but we cannot point to it, isolate it, or describe it in familiar terms. Even more unsettling is what dark energy implies for the future of observation itself. As expansion accelerates, distant galaxies recede faster and faster. Eventually, many will cross a horizon beyond which their light can no longer reach us. Over immense spans of time, the observable universe will grow quieter, emptier, and more isolated. This is not because the universe is losing content, but because dark energy is stretching space so efficiently that connections are being severed. regions that are observable today will become causally disconnected. Information that could once arrive will never do so again. In that sense, dark energy actively reduces what can be observed in the long term. It does not merely hide things by being invisible, it removes them from reach altogether. This casts observation itself as a temporary privilege. We exist at a time when galaxies are still visible, when cosmic structure can still be studied, when the history of the universe is still written across the sky. In the distant future, observers may find themselves in a universe where only their local group of galaxies remains visible, surrounded by darkness not because nothing exists, but because everything else has slipped beyond the horizon. Dark energy, then, is not just an absence. It is an influence that shapes both what exists and what can ever be known. It defines limits not just in space, but in time. Unlike dark matter, which adds hidden structure to the universe, dark energy subtracts potential connection. It stretches, separates, and isolates. It determines the ultimate scale of the observable universe, not just now, but forever. And yet, even with this profound impact, dark energy remains the least understood component of the cosmos. It does not fit neatly into existing theories. It resists intuitive explanation. It is inferred from large-scale behavior, not directly observed in any local experiment. This places us in a curious position. The dominant component of the universe governs its fate, shapes its geometry, and limits future observation, and we do not know what it is. If dark matter taught us that most of the universe's mass is invisible, dark energy teaches us something even more unsettling. Most of the universe's behavior is driven by something we cannot see, cannot touch, and cannot yet explain. Once this is accepted, the idea that we have observed only a small fraction of the universe is no longer abstract. It becomes unavoidable. The universe we describe with images and catalogues is a thin surface layer on top of deeper dynamics that remain hidden. Once the influence of dark energy is taken seriously, distance stops being a simple matter of how far something is from us. It becomes a question of access, not just whether light from a distant galaxy can reach us, but whether we could ever, even in principle, reach that galaxy ourselves or remain connected to it over cosmic time. And this is where the idea of unreachable galaxies quietly settles in, not as a dramatic science fiction concept, but as a straightforward consequence of how the universe expands. When we look at the night sky through powerful telescopes, we see galaxies scattered across enormous distances. Many of them are so far away that their light began its journey billions of years ago. We often speak about these galaxies as if they are distant neighbours, far away but still part of a shared cosmic environment. In reality, many of them already occupy a different category altogether. They are visible but unreachable, and in some cases they are not just unreachable now, but unreachable forever. This distinction is subtle, but important. There are galaxies whose light reaches us today, even though the space between us and them is expanding so rapidly that no signal sent from us now would ever arrive there. We are seeing their past, but we have no shared future. The connection is one way, and it is closing. This happens because expansion is not uniform in the way everyday motion is. When you throw a ball, it moves through space. When galaxies recede due to cosmic expansion, space itself stretches between them. This stretching does not obey the usual limitations of motion through space. On very large scales, the distance between objects can increase faster than light could traverse, not because anything is moving faster than light locally, but because space itself is growing. At relatively small distances, gravity holds galaxies together in groups and clusters. The Milky Way and its neighbouring galaxies form a bound system. They orbit one another and will remain connected despite cosmic expansion. But beyond these local regions, expansion dominates. Galaxies outside our local group are moving away from us, and the farther away they are, the faster that recession appears. there is a critical distance beyond which expansion overwhelms any possibility of future contact. Galaxies beyond this distance are receding so quickly that even light emitted now will never reach us in the future. Likewise, light we emit now will never reach them. They are already beyond our event horizon, not in the sense of a dramatic boundary you could point to, but in the sense of causal disconnection. The phrase event horizon is often associated with black holes, but in cosmology it has a different meaning. It refers to a boundary beyond which events cannot ever influence an observer. In an accelerating universe, such a horizon naturally arises. As space expands faster and faster, there are regions whose future signals are permanently cut off. This means there are galaxies we can see today that are already lost to us. Their light left them long ago, before expansion accelerated to its current rate. That light is still arriving now, like a delayed message sent before a door closed. But any new message sent after that point will never get through. It's worth sitting with that idea for a moment, because it challenges the way we instinctively think about the universe. Visibility feels like connection. If you can see something, it feels present, part of your world. But in cosmology, seeing does not imply access, it implies history. Those distant galaxies are not part of our present in any interactive sense. They are records of what once was. We observe them as they were, not as they are now, and certainly not as they will be. Even more striking is the fact that some galaxies are already beyond our ability to observe at all. They exist according to every reasonable cosmological model, but their light has never reached us and never will. They lie beyond the observable universe, permanently outside our past light cone. No amount of patience will bring their signals to us. No future telescope will reveal them. They are not hidden by dust or faintness. They are hidden by time and expansion. This creates a layered universe. There are nearby galaxies we can study in detail and potentially visit in principle, even if not in practice. There are distant galaxies we can see but never reach. And there are even more distant regions we can neither see nor reach, no matter how advanced our technology becomes. From a scientific perspective, this introduces a kind of asymmetry that feels unusual. Science is often framed as an open-ended process, where better tools eventually overcome current limits. In this case, the limits are not technological. They are built into the structure of space-time. No engine, no matter how powerful, can outrun the expansion of space beyond a certain scale. You could travel at speeds arbitrarily close to that of light, and still fail to reach regions that are being carried away faster than light can close the gap. The problem is not speed, it is geometry. This also reframes the idea of cosmic exploration. There is a tendency to imagine future civilizations spreading across the universe, colonizing galaxies, leaving marks on cosmic scales. While local expansion is possible within gravitationally bound regions, the universe as a whole does not offer unlimited reach. There is a finite region of space that will ever be accessible to any given observer. Beyond that, the universe continues, but not in a way that allows interaction. Exploration, in the cosmic sense, has hard boundaries. This does not diminish the universe. If anything, it emphasizes its scale. The universe is so large, and its expansion so profound, that even hypothetical civilizations with extraordinary capabilities would be confined to relatively small islands within it. From the standpoint of observation, this means that what we see today represents a fleeting window. There was a time when the observable universe was smaller, when fewer galaxies were visible. As time passed, more light arrived, and the observable region grew, but now, with accelerated expansion, the balance is shifting. In the very distant future, observers may see fewer galaxies than we do today. As expansion continues, distant galaxies will fade and disappear beyond the horizon. Their light will stretch, weaken, and eventually stop arriving altogether. The sky will grow emptier, not because galaxies vanish, but because they become unreachable. This gives our current moment a quiet significance. We live at a time when the universe is old enough for structure to have formed, but not so dominated by expansion that structure has slipped out of view. We can see billions of galaxies. That will not always be the case. For future observers in distant epochs, the universe may appear much smaller. They may see only their local group of galaxies surrounded by darkness. Without access to distant light, they might never infer the larger cosmic structure we now take for granted. This is not speculation in the loose sense. It follows directly from the observed acceleration of expansion. Dark energy does not just influence dynamics, it shapes the limits of knowledge over time. Even now, when astronomers map the distribution of galaxies, they are mapping only what is visible today. That map includes galaxies that are already causally disconnected. It is a map of the past, not of the accessible universe. This creates an interesting tension. The universe we describe in textbooks and documentaries includes regions that are not part of our future in any meaningful sense. They are part of our observational record, but not part of our interactive environment. When we speak about the universe as a whole, we often blur this distinction. We talk about billions of galaxies as if they are all equally part of the cosmic story. In one sense, they are. In another, they are divided by horizons that make some of them effectively irrelevant to our future. This is not a value judgment. It is a structural fact. It also means that there are questions we can ask that have no observational answers, not now and not ever. What lies beyond the furthest visible galaxies? Is the universe infinite? Does it repeat structures? Does it contain regions fundamentally different from what we observe? These questions may be meaningful, but they are not empirically accessible. We can build models, we can test consistency, we can rule out some possibilities, but direct observation is off the table. Those galaxies are not just far away, they are outside the domain of evidence. This challenges a common assumption about science, namely that everything that exists is in principle observable given enough time and effort. Cosmology shows that this is not the case. There are parts of reality that are permanently beyond observational reach, not because we are insufficiently clever, but because the universe is structured that way. And yet, this does not make the observed universe less valuable. It makes it more precious. The galaxies we can see are not a random sample. They are the ones whose light happened to reach us during a narrow window in cosmic history. Every image of the distant galaxy is an image of something we will never interact with. Every spectrum is a message from a place we will never visit. Observation becomes a form of contact without reciprocity. As we continue to think about how little of the universe we have actually observed, the idea of unreachable galaxies highlights a crucial point. Limitation is not just about what we cannot see, it is also about what we cannot ever touch, influence, or be influenced by. The universe is not a single connected stage where everything eventually interacts with everything else. It is a collection of regions with their own futures, drifting apart under the influence of expansion. And within this picture, our observable universe, impressive as it is, represents not just a small fraction of what exists, but a shrinking fraction of what will ever be accessible. This realization naturally leads to another question, one that shifts attention away from unreachable distances and back toward our own limitations. Even within the region we can see and will remain connected to, how much are we actually capable of detecting, and how much are we inferring rather than observing directly? Before we even reach the far edges of the observable universe, before distance, expansion, or cosmic horizons remove things from reach, there is a much closer boundary that quietly shapes everything we know. It sits not billions of light years away, but right here at the interface between the universe and the tools we use to perceive it. This boundary is defined by the limits of telescopes, instruments, and ultimately by the limits of human senses themselves. It's easy to forget that every observation, no matter how advanced, is mediated. We do not encounter the universe directly. We encounter signals that have been filtered, transformed, amplified, and interpreted. Even the most powerful telescope is not an extension of the eye in the way binoculars are. It is a translator, converting forms of information that would otherwise pass through us, unnoticed, into something we can record and analyse. Human senses evolved for survival on Earth, not for understanding the cosmos. Our eyes are tuned to a narrow range of light wavelengths because that range happens to pass efficiently through Earth's atmosphere, and because it aligns with the energy output of our Sun. This coincidence is useful for life, but deeply limiting for astronomy. Most of the universe does not shine in visible light. Most cosmic processes occur outside the range our eyes can detect. If we relied only on unaided vision, our picture of the universe would be extremely small and misleading. We would see a handful of nearby stars, a faint band of the Milky Way, a few bright planets, and little else. Galaxies beyond our own would be invisible. Vast clouds of gas would go unnoticed. The structure of the universe would remain entirely hidden. Telescopes expand this range, but not without trade-offs. Every telescope is designed with specific goals and specific limitations. Some collect visible light, others infrared, radio waves, ultraviolet radiation, X-rays, or gamma rays. Each window reveals certain features and obscures others. There is no universal instrument that captures everything at once. Even within a single wavelength range, there are constraints. Resolution limits how fine a detail can be seen. Sensitivity determines how faint a signal can be detected. Field of view restricts how much of the sky can be observed at once. Time limits how long an object can be monitored. All of these factors shape what we are able to notice and what remains hidden. Resolution, for instance, is not simply a matter of magnification. It is constrained by the size of the telescope's collecting area and by the wavelength of light being observed. Shorter wavelengths allow finer detail, but they are harder to collect and often blocked by Earth's atmosphere. Longer wavelengths travel more easily, but blur fine structure. Every observation balances clarity against reach. Sensitivity introduces another layer of limitation. The universe is filled with extremely faint signals. By the time light reaches us from distant or diffuse sources, it may consist of only a few photons per second hitting a detector. Distinguishing that signal from background noise requires long observation times, careful calibration, and statistical analysis. Even then, uncertainty remains. Noise comes from many sources. Detectors themselves produce random fluctuations. Cosmic background radiation fills space. Foreground objects interfere. Earth's atmosphere introduces turbulence and absorption. Even space-based telescopes must contend with thermal noise, radiation damage, and instrumental drift. Observation is never a clean process. It is always an exercise in separating signal from clutter. Human interpretation adds another layer. Data does not arrive as a clear picture. It arrives as streams of numbers, counts, intensities, and frequencies. Those numbers must be processed, filtered, and translated into images or models. Choices made during that process influence what stands out and what fades into the background. This does not mean that astronomers manipulate results arbitrarily. It means that observation is an active process. Decisions about contrast, colour mapping, averaging, and noise reduction all shape the final representation. The stunning images often shared publicly are not photographs in the everyday sense. They are visualizations designed to make invisible information comprehensible. That comprehensibility comes at a cost. Features may be emphasized or suppressed. Colors may represent wavelengths the eye cannot see. Structures may be clearer in the image than they are in the raw data. These images are truthful, but they are not neutral. Beyond instrumentation, there is the issue of scale. Telescopes observe either very small regions in great detail or very large regions with limited detail. Studying the universe requires switching constantly between these modes. We zoom in to understand local processes and zoom out to see large-scale patterns, but we can rarely do both at once. This creates gaps. There are regimes of scale that are poorly observed because they fall between the strengths of existing instruments. Objects that are too large and diffuse for detailed study and too small to stand out in surveys can slip through observational cracks. time introduces another limitation. Many cosmic processes unfold over millions or billions of years. We observe only snapshots. We infer evolution by comparing different objects at different stages, not by watching a single system change in real time. This works well statistically, but it hides individual histories. Other processes are too fast. Brief bursts of energy, transient events, or sudden changes may occur when no instrument is pointed in the right direction. Astronomers rely on networks of detectors and automated alerts, but even then, many events are missed entirely. Then there is the fundamental issue of accessibility. Telescopes detect signals that reach us. They cannot detect things that produce no signals we know how to measure. If a component of the universe interacts only through gravity, or through forces we have not yet identified, it will remain invisible regardless of telescope size. This is where the limits of human senses extend into the limits of human concepts. We tend to assume that if something exists, it must leave some detectable trace. But detection depends on interaction. If interaction is weak or non-existent with our instruments, existence does not translate into observation. Dark matter already demonstrates this. Dark energy goes even further. But there may be other components of reality that lie entirely outside our current observational frameworks. Not because they are rare, but because they do not participate in the interactions we know how to measure. There is also the constraint of perspective. We observe from one location, moving along one world line through space-time. We cannot step outside the universe to view it from above. We cannot compare different cosmic vantage points directly. Our observations are inherently local, even when they concern distant objects. This local perspective affects interpretation. When we assume the universe looks roughly the same everywhere, we do so because observations within our reach suggest uniformity. But uniformity beyond our horizon is an assumption, not an observation. It is a reasonable one, supported by theory and consistency, but it remains an inference. Human cognition adds further limitations. Our brains are pattern-seeking, story-driven systems. We look for coherence, causality, and simplicity. These tendencies are useful, but they can also mislead. We may prefer models that are elegant over models that are messy, even if reality favours the latter. We also struggle with extremes. Very large numbers, very small probabilities, and very long time scales are difficult to internalize. We rely on analogies that inevitably distort. When we say something is like something else, we gain understanding at the cost of precision. All of this means that the universe we describe is filtered through layers of limitation, physical limits of signal propagation, instrumental limits of detection, cognitive limits of interpretation. Each layer narrows the slice of reality we can meaningfully access. Despite these constraints, progress has been extraordinary. Telescopes today can detect light that has travelled for nearly the entire age of the universe. Instruments can measure temperature differences in cosmic radiation to astonishing precision. Gravitational waves allow us to sense events that emit no light at all, and yet each new capability reveals new blind spots. As we open one window, we notice how many others remain closed. Observing the universe is not a march toward completion. It is a continual negotiation with limitation. This negotiation shapes the question at the heart of this series. How little of the universe have we actually observed? The answer is not just a small fraction of space. It is also a small fraction of possible information. We observe what our tools allow, what physics permits to reach us, and what our minds can process. Most of the universe's content does not glow. Most of its history unfolds beyond direct reach. Most of its behavior is inferred rather than witnessed. Even within the observable universe, what we see is a curated subset, shaped by the intersection of cosmic processes and human capability. Understanding this does not diminish science, it clarifies its scope. Science does not promise total access to reality. It promises the best possible understanding given the constraints of the universe and ourselves. Once that perspective settles, another realization naturally follows. If our observations are so limited, then much of what we claim to know about the universe is not observed directly at all. It is reconstructed. It is inferred from patterns, models, and consistency across data. And that raises the next quiet question. When we talk about the universe beyond what we see, how much of our understanding is observation, and how much is inference filling in the gaps left by darkness and distance? At some point, once you've followed observation as far as it will reasonably go, you begin to notice a quiet shift in how knowledge is constructed. The language changes subtly. Words like see and detect appear less often, replaced by phrases like suggests, indicates, is consistent with, or best explained by. This is the point where direct observation gives way to inference, not as a fallback or a failure, but as the primary way we understand most of the universe. Inference often sounds less solid than observation, especially in everyday language. To infer can feel like guessing, filling in blanks, or making educated leaps. But in science, inference is neither casual nor optional. It is a disciplined process, governed by evidence, constrained by mathematics, and constantly tested against new data. Without inference, modern cosmology would simply not exist. Most of what we say about the universe beyond our immediate surroundings is inferred rather than observed in the strict sense. We do not observe cosmic history unfolding, we reconstruct it. We do not observe the internal composition of distant stars, we infer it from their spectra. We do not observe the total mass of galaxies, we infer it from how things move. Observation provides fragments, inference connects them into something coherent. This distinction matters because it shapes the confidence and the limits of what we claim to know. When we say the universe is expanding, we are not watching it expand the way we watch a balloon inflate. We are measuring distances and velocities at different scales and inferring expansion as the best explanation that fits all the data. When we say the universe had a hot, dense beginning, we are not observing that beginning directly. We are inferring it from patterns left behind. Inference becomes necessary whenever direct access is impossible, and in cosmology, direct access is almost always impossible. The universe is too large, too old, and too dynamic to be fully observed in real time. Signals arrive late, processes unfold slowly or too quickly. Regions lie beyond reach. Inference is not a shortcut. It is the only path available. Consider something as basic as distance. We cannot stretch a measuring tape across space. We infer distance using indirect methods. We compare brightness, measure redshift, use known physical relationships, and build a ladder of techniques, each calibrated against the others. Every rung of that ladder rests on inference. Each step is justified, tested, and refined. But none are purely observational in the everyday sense. The same is true for mass. We cannot weigh a galaxy. We infer its mass by observing how fast stars orbit within it, how it bends light, how it influences nearby objects. When these methods agree, confidence increases. When they disagree, models are revised. Inference is not arbitrary. It is constrained by consistency. Even the structure of the universe on the largest scales is inferred. We do not observe the cosmic web directly as a three-dimensional object. We infer it from galaxy surveys, gravitational effects, and simulations that match observed distributions. The web itself is mostly invisible. What we see are luminous traces embedded within it. Time itself becomes an inferred quantity at cosmic scales. We do not observe the age of the universe ticking upward. We infer it from expansion rates, radiation signatures, and models of cosmic evolution. Different lines of evidence converge on similar values, lending credibility, but the age remains a reconstructed property, not a directly observed one. This reliance on inference is sometimes uncomfortable for people outside science, because it feels less certain than direct observation. But in many ways, inference can be more reliable than raw observation, because it integrates multiple sources of evidence. A single observation can mislead. A well-supported inference must account for many observations at once. That said, inference always carries assumptions. Some are explicit, others are implicit. Recognizing them is part of scientific rigor. For example, when cosmologists assume that the laws of physics are the same everywhere, they do so because observations within our reach support that assumption. But it remains an assumption. It cannot be tested beyond the observable universe. Similarly, when scientists infer the existence of dark matter, they assume that gravity behaves the same on galactic scales as it does locally. Alternatives exist, but they struggle to explain the full range of observations without introducing other complications. The inference is strong, but it is still an inference. Dark energy pushes this even further. Its existence is inferred almost entirely from the expansion history of the universe. We do not observe dark energy interacting with anything locally. We infer it because without it, the observed acceleration makes no sense. It is a placeholder for an effect whose cause remains unknown. This highlights an important aspect of inference. Sometimes we infer entities, sometimes we infer properties, sometimes we infer relationships, and sometimes we infer the need for new concepts altogether. Inference is not always about filling in missing details. Sometimes it is about recognizing that existing frameworks are incomplete. In everyday life, inference is often subconscious. You hear footsteps and infer someone is approaching. You see dark clouds and infer rain. These inferences are based on experience and probability. In science, inference is formalized, quantified, and tested. Probabilities are calculated, uncertainties are stated, alternative explanations are considered. Despite this rigor, inference is never final. New observations can overturn old inferences. This is not a flaw, it is a feature. It allows knowledge to adapt as evidence accumulates. One of the most striking examples of inference in cosmology is the reconstruction of the early universe. We infer conditions billions of years ago based on patterns we observe today. Slight variations in cosmic background radiation, distributions of galaxies, and elemental abundances all point to a universe that was once hot, dense, and nearly uniform. No single observation proves this. Together, they form a coherent picture. That coherence is key. Inference gains strength when independent lines of evidence converge. When different observations using different methods point to the same conclusion, confidence grows. This is why cosmology, despite its reliance on inference, is considered a robust science. Still, it is important to distinguish between what is inferred, because it must be, and what is inferred, because it is convenient. Good science resists the latter. It demands that inferences earn their place by explaining more than they assume. This is also where humility enters. When scientists say the data suggests, they are acknowledging the provisional nature of inference. They are leaving room for revision. They are resisting the temptation to present inference as certainty. From the perspective of how little of the universe we have actually observed, this reliance on inference is revealing. It shows that observation alone accounts for a surprisingly small fraction of our understanding. Most of the universe, as we describe it, exists as a carefully reasoned extension beyond what we can directly detect. This does not mean the universe is imaginary beyond our sight. It means that our access to it is mediated by logic rather than direct perception. We trust inference because it works, because it predicts new observations, because it explains patterns that would otherwise remain mysterious. But trust is not the same as completeness. Inference fills gaps, but it also highlights them. Every inferred component marks a place where observation stops and reasoning begins. Each such place is a reminder of limitation. It is also worth noticing that inference shapes narrative. The way we tell the story of the universe depends on inferred connections between events. We speak of cosmic evolution as a sequence, even though we never observe that sequence directly. We reconstruct it from snapshots taken at different distances and times. This reconstruction is powerful, but it is also sensitive to interpretation. Small changes in assumptions can lead to different narratives. Most are constrained tightly by data, but some remain open. Debates persist not because scientists lack data, but because inference allows multiple explanations to coexist when evidence is incomplete. There is also a psychological aspect to inference. Humans are comfortable with stories. We like explanations that feel continuous and complete. Inference allows us to build such stories, but it also tempts us to smooth over uncertainties. Good science resists that temptation by keeping uncertainties visible. In popular discussions, inferred knowledge is often presented without qualification. This can create the impression that everything is observed directly, that the universe has been fully mapped and explained. The reality is more nuanced. Much of what we know is the best current explanation, not a final answer. This nuance is not a weakness. It is the reason science progresses. If inferences were treated as unchangeable facts, new evidence would be ignored. By holding inference lightly, science remains open to revision. From a broader perspective, inference is what allows us to talk meaningfully about things beyond our immediate reach. Without it, the universe would shrink to the size of our senses. With it, the universe expands into a vast, partially known, partially unknown whole. And yet, inference has limits. There are questions for which inference may never provide firm answers. What lies beyond the observable universe may remain permanently speculative. The ultimate nature of dark energy may resist explanation within existing frameworks. Some aspects of reality may simply not leave accessible traces. Recognizing this does not diminish curiosity. It refines it. It directs attention toward questions that can be meaningfully explored and away from false certainty. The role of inference becomes even more central, because once we accept that much of the universe is inferred rather than observed, another question emerges naturally. How far back can inference take us? How much of the universe's earliest history can we reconstruct? And where do the traces fade into ambiguity? When attention turns toward the earlier stages of the universe, observation becomes something closer to archaeology than watching. There is no continuous record, no unfolding sequence that can be followed moment by moment. Instead, there are traces, faint signals, patterns left behind by conditions that no longer exist. Everything we say about the early universe is built from these remnants, interpreted through theory and constrained by physics, always aware that we are working from echoes rather than direct experience. The phrase early universe can be misleading if it sounds like a specific place or a clearly defined era. In reality, it refers to a range of conditions that changed rapidly over time. The universe did not simply switch from early to late. It transitioned through phases, each governed by different dominant processes, each leaving different kinds of imprints. Our ability to glimpse these phases depends entirely on what signal survived long enough to reach us. The earliest period we can talk about with any observational grounding begins not at the very beginning, but slightly after it. There is a hard limit here, and it is not philosophical, it is physical. In the earliest moments, the universe was so hot and dense that no stable structures could exist, and no signals we can detect today could propagate freely. Light could not travel without immediately interacting with charged particles. Information was trapped in a tightly coupled plasma. This means that for a significant stretch of the universe's infancy, there is no direct observational access at all, not because our instruments are insufficient, but because the universe itself was opaque. Photons could not move independently. Space was filled with matter and radiation in constant interaction. Any information from that time was scrambled beyond recovery. Only when the universe cooled enough for electrons to bind with nuclei did this change. At that moment, light was finally able to travel freely. Photons decoupled from matter and began their long journey through expanding space. Those same photons are still arriving today, stretched and cooled, carrying with them a snapshot of the universe at that moment. This is the earliest direct glimpse we have. It is not an image of objects, but a record of conditions. Slight variations in temperature and density imprinted across the sky. Tiny differences that later grew into galaxies and clusters. This background radiation is often described as a baby picture of the universe, but even that metaphor understates the abstraction involved. What we see is not a scene. It is a statistical pattern. From that pattern, scientists infer an enormous amount: the age of the universe, its overall geometry, its composition, the relative amounts of ordinary matter, dark matter, and dark energy, the initial conditions that allowed structure to form. None of this is directly visible. It is reconstructed from subtle variations measured with extreme precision. Before this moment of transparency, everything becomes more speculative. Theories extend backward, guided by well-tested physics, but no longer anchored by direct observation. We can describe what likely happened based on how matter and energy behave under extreme conditions. We can test these descriptions indirectly by seeing whether they lead to the universe we observe later. But we cannot confirm them by looking. This is where the word glimpse earns its place. We do not see the early universe in the way we see galaxies. We infer it from a single ancient signal and from the consistency of physical laws across time. The further back we push, the thinner the evidence becomes. Even within the earliest observable snapshot, resolution is limited. We cannot zoom in indefinitely. There is a smaller scale at which meaningful information is preserved. Below that scale, random fluctuations dominate. This sets a fundamental limit on how much detail about the early universe can ever be recovered. As we reconstruct this early period, one of the most striking features is its simplicity. Compared to the universe today, with its complex structures and varied environments, the early universe was remarkably uniform. Matter was distributed almost evenly. Differences existed, but they were tiny. Without amplification, nothing interesting would have happened. The fact that anything interesting did happen requires explanation. Those tiny differences had to grow. Gravity had to pull matter together. Dark matter had to clump early, providing a scaffold for ordinary matter to follow. All of this is inferred from how structure looks today. We reverse engineer the past from the present. This reverse engineering is powerful, but it is also sensitive. Small changes in initial conditions can lead to very different outcomes. That means our picture of the early universe is constrained, but not uniquely determined. Multiple histories could, in principle, lead to similar present-day structures. Scientists narrow the possibilities by demanding consistency across many observations. The distribution of galaxies, the abundance of light elements, the background radiation pattern. When a model fits all of these at once, it gains credibility. When it fails at any point, it is revised or discarded. Still, there are unanswered questions that sit squarely in the early universe. Why were the initial conditions the way they were? Why was the universe so uniform? Why did it contain just the right mix of components to allow structure to form? These questions cannot be answered by observation alone. They point toward deeper principles or earlier phases we cannot see. One such idea proposes a period of extremely rapid expansion very early in the universe's history. This expansion would explain uniformity, flatness, and the origin of tiny fluctuations. It would stretch space so quickly that regions once close became widely separated. This idea fits observations remarkably well, but the mechanism behind it remains speculative. Here again, inference reaches its limits. The idea is compelling because it explains multiple features at once, but it rests on physics that has not been directly tested. We infer its occurrence because the universe looks as if it happened. That is strong, but not final. Beyond that hypothetical period lies an even deeper mystery, the very beginning. A point where current theories break down, where space and time as we understand them may not apply. We can write equations that point toward a beginning, but those equations stop making sense at extreme densities and energies. At that point, words like before and after lose their usual meaning. Time itself becomes uncertain. Observation becomes impossible in principle, not just in practice. There may be no signals to detect, no traces to follow, no framework within which observation could even be defined. This does not mean there was nothing. It means our concepts reach their limit. The universe does not guarantee that it will be understandable in all respects. It only guarantees that it behaves consistently within the regimes we can test. What makes the early universe especially relevant to the question of observation is that it shows how knowledge thins out as we move away from the present. The universe becomes less detailed, less accessible, more reliant on inference. Even the earliest glimpse we have is already a reconstruction, not a direct view. This also reshapes how we think about certainty. When people talk about the early universe, it can sound as if we have a complete story, neatly laid out from beginning to end. In reality, the story has clear chapters and missing pages. Some parts are well supported, others are provisional. Some may never be filled in. This does not undermine the parts we do understand. It contextualizes them. It reminds us that cosmology is not a finished map, but an evolving framework, refined as new data arrives and old assumptions are tested. It is also worth noticing how dependent our understanding of the early universe is on the fact that signals survived at all. If the universe had remained opaque for longer, or if expansion had proceeded differently, those early traces might have been erased. The fact that we can glimpse anything at all is contingent. That contingency gives the present moment a quiet significance. We exist at a time when the universe is transparent enough, structured enough, and calm enough for its early history to still be readable. That will not always be the case. As expansion continues, signals will redshift further, weaken, and eventually fade beyond detection. The early universe will become harder to study, not easier. Knowledge of cosmic origins is not guaranteed to persist indefinitely. This brings the focus back to the central theme. How little of the universe have we actually observed? When it comes to the early universe, the answer is especially stark. We have not observed it unfolding. We have not observed its beginning. We have not observed most of its transitions directly. We have inferred them from what remains. Those inferences are impressive, coherent, and deeply constrained by data. But they are still inferences. They mark the boundary between what the universe has shown us and what we have reconstructed. And once that boundary is acknowledged, another question emerges naturally. If the early universe itself is only partially accessible, and if vast regions of space lie beyond observation, then what lies beyond both distance and time? What possibilities exist outside our cosmic horizon, and how should we think about them without drifting into speculation untethered from evidence? Once the limits of observation and inference are both clearly in view, attention naturally drifts outward again, not toward anything we can see, but toward what lies beyond seeing altogether. This is where the idea of a cosmic horizon stops being a technical term and becomes something more quietly unsettling. The horizon is not just a line on a diagram. It represents the boundary between what can ever affect us and what cannot, between what belongs to our observable story and what exists without any possibility of direct confirmation. The cosmic horizon is not a physical edge. It is not a wall, a shell, or a border you could approach. It is a consequence of time, expansion, and the finite speed at which information travels. It exists because the universe has a history, and because that history unfolds in a way that limits connection. Beyond it, space continues, but causality does not. When we speak about possibilities beyond this horizon, we are stepping into a domain where observation ends completely. Not temporarily, not due to current technological limits, completely. Nothing beyond the cosmic horizon has ever influenced us, and under current understanding, nothing beyond it ever will. This raises an immediate question. If something can never affect us and can never be observed, in what sense does it matter? This is not a philosophical trick. It is a practical concern for science. Science relies on evidence. Evidence relies on interaction. Beyond the horizon, interaction is absent, and yet science still speaks about what might exist there, not casually and not without restraint, but thoughtfully, guided by models that extend beyond observation while remaining anchored to what we know within it. One of the simplest possibilities is also the most conservative. The universe beyond the horizon may look much like the universe within it. Same laws of physics, same large-scale structure, same mixture of components. From this perspective, the observable universe is just one patch of a much larger whole, no different in kind from any other patch. This assumption is not arbitrary. It arises from the remarkable uniformity observed within our horizon. No matter which direction we look, the universe appears broadly similar when viewed on sufficiently large scales. There are local variations, clusters, voids, filaments, but statistically, the universe looks the same in every direction. If the laws of physics appear consistent everywhere we can observe, it is reasonable to assume that this consistency extends beyond our horizon as well. Reasonable, but not provable. This assumption is a foundation of modern cosmology, and without it, coherent models become much harder to build. However, reasonable does not mean guaranteed. There is no observational requirement that regions beyond our horizon must resemble our own. Uniformity within the observable universe does not logically demand uniformity everywhere. It merely suggests it as the simplest explanation. Another possibility is that the universe extends far beyond our horizon, but remains finite in total size. In this view, space might curve back on itself in subtle ways, forming a closed geometry. If this were the case, the universe could be vast yet limited, like the surface of a sphere but in higher dimensions. Detecting such curvature would require observing repeating patterns or specific distortions across the sky. So far, observations suggest that the universe is very close to geometrically flat, but very close is not the same as exact. The universe can be enormous and still finite, with curvature so gentle that it remains undetectable within our horizon. If the universe is finite, then beyond our horizon lie regions that exist simultaneously with us, governed by the same physics, but permanently inaccessible. They are not elsewhere in time, they are elsewhere in space, separated by distance that no signal can cross. There is also the possibility that the universe extends infinitely. In that case, the observable universe would be an infinitesimal fraction of what exists. No matter how much we observe, the unobserved would always outweigh it. An infinite universe carries strange implications. In an infinite space governed by consistent laws, any configuration of matter that is physically possible should occur somewhere, given enough volume. This leads to unsettling ideas about repetition. Regions similar to our own, perhaps even nearly identical, could exist unimaginably far away, beyond any possibility of contact. These ideas are mathematically consistent, but observationally unreachable. They cannot be tested directly. Their appeal or discomfort comes from extrapolation, not evidence. Some cosmological models go further still. They suggest that what lies beyond our horizon may not just be more of the same universe, but regions with different properties altogether, different values of physical constants, different laws, different outcomes of early cosmic processes. In these models, our observable universe is one domain among many. The cosmic horizon marks the boundary of our domain, not the boundary of existence. Beyond it may lie regions that expanded differently, cooled differently, and evolved under different conditions. These ideas often arise when scientists try to explain why the universe has the properties it does. Why do physical constants take the values they do? Why does the universe allow structure, chemistry, and long-lived stars? Some explanations appeal to necessity, others appeal to selection. In selection-based explanations, many regions exist with varying properties, and observers arise only in regions where conditions permit complexity. From this perspective, our universe looks special, not because it is unique, but because we are here to observe it. This line of reasoning is controversial, not because it is illogical, but because it stretches the definition of testability. If other regions are permanently beyond observation, can claims about them ever be scientific in the usual sense? Opinions differ. Some argue that if a model makes testable predictions within our observable universe, then its unobservable implications are acceptable. Others argue that science should restrict itself to what can, in principle, be observed. This debate highlights a deeper tension. Cosmology sits at the edge of what science can do. It deals with a single system, the universe, with no external reference point. It cannot perform controlled experiments on initial conditions. It must infer global properties from local observations. Beyond the cosmic horizon, this tension becomes unavoidable. Possibilities multiply. Constraints weaken. Imagination threatens to outrun evidence. And yet, ignoring these possibilities entirely would also be unsatisfying. The horizon exists. It divides what we can observe from what we cannot. It is natural to ask what lies beyond it, even if answers must remain provisional. Another possibility worth considering is that the horizon itself is not fixed in the deepest sense. While our current understanding suggests permanent disconnection due to accelerated expansion, this conclusion depends on the nature of dark energy. If dark energy evolves over time, the horizon could change. Regions currently beyond reach might become accessible or vice versa. At present, observations are consistent with a universe where accelerated expansion continues indefinitely. But consistency is not certainty. If dark energy behaves differently in the far future, the structure of horizons could change in ways we cannot currently test. Even so, any such change would unfold over timescales far beyond human history. For all practical purposes, the cosmic horizon defines a permanent limit on observation. There is also a conceptual shift that happens here. Beyond the horizon, the universe ceases to be an object of observation and becomes an object of implication. We talk about it because it follows logically from our models, not because we have evidence from those regions themselves. This is not unusual in science. We talk about the interiors of stars we cannot see. We talk about the cores of planets we cannot access. We talk about early phases of cosmic history we cannot observe directly. The difference here is scale. Beyond the horizon, the entire region is inaccessible, not just its details. That scale forces restraint. Good cosmology treats statements about beyond the horizon with caution. It distinguishes between what is strongly implied, what is weakly suggested, and what is speculative. What is strongly implied is that space continues beyond the horizon. There is no evidence that the universe ends at the observable boundary. What is weakly suggested is that large-scale properties may be similar. What is speculative is almost everything else. This does not make speculation useless. Speculation drives theory. It motivates questions. It highlights gaps in understanding. But speculation must remain clearly labelled as such. From the perspective of how little of the universe we have actually observed, possibilities beyond the cosmic horizon drive the point home. Even if we mapped every galaxy, measured every signal, and understood every process within the observable universe perfectly, we would still be dealing with a subset of reality. The horizon does not just limit observation, it limits verification. There are truths about the universe, if that word applies, that we may never be able to confirm or deny. This is not a failure of curiosity. It is a structural feature of a universe with finite age and accelerated expansion. At the same time, it reframes what knowledge means. Knowledge does not require total access. It requires coherence, consistency, and predictive power within the domain that is accessible. Beyond that domain, humility becomes part of understanding. It is also worth noticing how this realization affects perspective. Humans often place themselves at the center of things by default. The cosmic horizon removes that temptation. It shows that our view is local, contingent, and incomplete. And yet, incomplete does not mean insignificant. The observable universe is vast enough to support deep questions, rich structure, and meaningful understanding. The fact that more exists beyond it does not reduce the value of what we can study. If anything, it adds context. It reminds us that the universe is not tailored to our comprehension, that what we see is not all that is, that existence is larger than evidence. If so much lies beyond observation, and if even within our horizon most of what exists is invisible or inferred, then a final question begins to take shape. Why does any of this matter? Why does understanding a universe we cannot fully observe still carry meaning? And what does that limited knowledge offer us as observers embedded within a small, accessible patch of an immeasurable whole? At this point, after tracing distance, darkness, inference, horizons, and the vast amount of the universe that remains unseen, an almost unavoidable question surfaces. If so much of the universe lies beyond observation, beyond reach, and perhaps beyond explanation, then why does any of this knowledge matter at all? Why invest effort, imagination, and care into understanding something that will always remain partial? This question is not cynical, it is reasonable. It arises naturally once the limits are clear, and answering it does not require grand declarations or dramatic conclusions. It requires a careful look at what knowledge actually does, even when it is incomplete. First, knowing so little still matters because partial knowledge is not the same as ignorance. There is a tendency to think of understanding as binary. Either you know something fully, or you do not know it at all. The universe does not operate on those terms. Almost everything we meaningfully understand is understood partially. Weather, biology, medicine, even our own minds. Incomplete knowledge still guides action, shapes expectations, and improves decision-making. Cosmology works the same way. Knowing that the universe is expanding, even without knowing why dark energy exists, fundamentally changes how we interpret distance, age, and motion. Knowing that most matter is invisible reshapes how we understand galaxies, structure, and gravity. These insights are not undermined by their incompleteness. They are enabled by it. Understanding limits also prevents false certainty. Before the expansion of the universe was established, the cosmos was often assumed to be static and eternal. That assumption felt reasonable, but it was wrong. Recognizing that observation has limits makes scientists cautious. It encourages questions rather than closures. It keeps theories flexible. This matters because false certainty is more dangerous than admitted ignorance. When limits are ignored, models harden into beliefs. When limits are acknowledged, models remain tools. Knowing so little still matters because it places humans correctly within the universe. Not at the center, not at the edge, but embedded within it. Historically, humanity has often assumed that what is most obvious to us is most important. The sun must orbit Earth because it appears to do so. The stars must be close because they appear fixed. The universe must be small because we can see its brightest parts. Each time those assumptions were overturned, it was not because people became less curious, but because curiosity was applied more carefully. Realizing how little we observe continues that tradition. It counters the instinct to mistake familiarity for completeness. There is also a deeper reason. Knowledge of the universe shapes how we understand time. Human lives are short, civilizations are fragile. Against cosmic timescales, everything familiar is temporary. This is not meant to diminish meaning, it reframes it. When you understand that the universe existed for billions of years before you and will continue for billions after, daily concerns shift slightly. Not disappear, but loosen. Perspective expands. Urgency softens. Even knowing that most of the universe is unreachable does something subtle. It reminds us that not everything is meant to be grasped, owned, or resolved. Science at its best does not promise control. It offers orientation. Knowing so little still matters because the act of knowing is cumulative. Each generation inherits not just answers, but better questions. Cosmology today exists because earlier thinkers asked questions they could not fully answer. Their partial insights laid foundations. Even wrong ideas narrowed possibilities. Even failed models clarified constraints. Understanding the universe as mostly unobserved does not halt inquiry. It refines it. It tells future scientists where observation ends and where creativity must be disciplined by evidence. There is also a practical dimension. Technologies that emerge from studying the universe have reshaped everyday life. Precision timekeeping, navigation systems, imaging technologies, data analysis methods. None of these required a complete understanding of the cosmos. They emerged from partial understanding applied carefully. Even dark matter and dark energy research drives advances in instrumentation, computation, and theory that ripple outward. The universe does not need to be fully known to be useful. It needs to be engaged with honestly. Another reason this knowledge matters is that it protects against misleading narratives. In the absence of scientific humility, it becomes easy to fill gaps with unfounded certainty. Stories that claim total understanding, hidden purposes, or privileged insight thrive where limits are denied. By contrast, acknowledging how little we observe encourages intellectual restraint. It distinguishes between evidence-based claims and speculation. It allows wonder without surrendering rigor. There is also a quiet emotional impact. Knowing that most of the universe is unseen does not make existence smaller. It makes it larger. It replaces the idea of a finished map with the idea of an open landscape. Mystery becomes a feature, not a flaw. This matters because humans respond differently to mystery depending on how it is framed. When mystery is treated as a failure, it breeds frustration. When treated as an invitation, it fosters curiosity. Curiosity does not require certainty. It requires space. Understanding the limits of observation also matters because it reveals how fragile knowledge can be. Observational windows open and close over cosmic time. We exist during a period when the universe is readable in ways it will not always be. Distant galaxies are still visible. Early cosmic signals are still detectable. In the far future, much of this information will fade beyond reach. That makes present understanding historically contingent. It reminds us that knowledge is not guaranteed. It must be recorded, transmitted, and preserved. Scientific literacy is not just about progress, it is about stewardship. Knowing so little still matters because it reshapes how we talk about certainty in other domains. When science openly acknowledges limits, it models a way of thinking that is cautious without being paralyzed, confident without being rigid. This way of thinking extends beyond cosmology. It influences how uncertainty is handled in medicine, climate science, economics, and risk assessment. Knowing that incomplete knowledge can still be meaningful counters the false choice between total certainty and total ignorance. There is also an ethical dimension. Recognizing limits tempers arrogance. It discourages the assumption that everything exists for human use or understanding. It encourages respect for complexity. This does not mean withdrawing from inquiry. It means approaching inquiry with proportional expectations. On a more personal level, knowing how little we observe can be grounding. It shifts attention away from the need to resolve everything. It allows unanswered questions to coexist with daily life. It makes room for curiosity without anxiety. Not every question must be answered to live meaningfully. Some questions enrich life precisely because they remain open. This perspective also reframes progress. Progress does not mean eliminating mystery. It means moving the boundary thoughtfully, knowing that it will always exist. Even the recognition of dark matter and dark energy represents progress, not because they solved everything, but because they clarified what needs explaining. They replace confusion with structured ignorance, which is a step forward. Structured ignorance matters. It tells us what we do not know and why we do not know it. That is far more useful than vague uncertainty. There is also a narrative reason this matters. Humans are storytelling beings. We understand ourselves through stories about origins, contexts, and futures. Cosmology offers a story that is not centered on humans, not complete, and not comforting in a simple way, and yet it is honest. That honesty has value. It situates human stories within a larger framework without reducing them to insignificance. Meaning does not require centrality, it requires context. Knowing that we inhabit a small, observable patch of a vast universe does not strip life of meaning. It frees meaning from the burden of cosmic importance. Meaning becomes local, relational, lived. Finally, knowing so little still matters because it keeps science human. Science is not a machine that produces final answers. It is a process carried out by limited beings trying to understand a reality that exceeds them. That tension is not a flaw, it is the source of its integrity. When scientists admit limits, they are not surrendering authority, they are demonstrating honesty, and honesty matters. As this reflection settles, the question shifts one last time, not toward what lies beyond and not toward what remains unseen, but toward how we carry this knowledge forward. If the universe is mostly unobserved, mostly inferred, and partly unreachable, then what does it mean to live within the part we can see? How do we return from these vast scales to our immediate experience without losing the perspective gained? After spending so much time with distances that stretch beyond intuition, with components of the universe that never reveal themselves directly, and with horizons that permanently limit what can be known, it becomes natural to ease back towards something more immediate, not by abandoning the larger picture, but by letting it settle into the background where it can quietly change how familiar things feel. The universe does not require us to remain mentally suspended at its largest scales. We are allowed to return slowly to where we actually live. This return does not erase what came before, it reframes it. We began with the idea that we observe very little of the universe compared to what exists. That remains true. Most of the universe's matter does not emit light. Most of its energy does not clump into structures. Vast regions lie beyond causal contact. Even the parts we can see are observed indirectly, delayed by time, filtered through instruments, reconstructed through inference. None of that disappears when we turn our attention back toward Earth. What changes is how that knowledge sits with us. From the ground, the sky does not announce its complexity. It looks calm, predictable. Stars rise and set. The moon moves through phases. The sun follows a familiar arc. From this vantage point, the universe feels stable, even modest. And that feeling is not wrong. It is appropriate to the scale at which human lives unfold. The mistake would be to assume that because something feels manageable, it is complete. Understanding how little we observe does not demand constant awe or existential weight. It does not require standing outside at night thinking about expansion or dark energy. Instead, it subtly alters assumptions. It loosens the idea that what is visible is what matters most. It encourages patience with unanswered questions. It allows uncertainty to exist without urgency. There is a tendency, especially in popular discussions of cosmology, to treat cosmic knowledge as something that should overwhelm everyday concerns. As if understanding the scale of the universe should make ordinary life feel trivial. In practice, the opposite often happens. When scale is properly understood, everyday life becomes more grounded, not less. A small, safe view is not a failure of imagination. It is a biological necessity. Human nervous systems are not built to process cosmic immensity continuously. We need bounded environments, predictable rhythms, and familiar references. The fact that the universe is vast does not mean we are meant to experience it directly at that scale. Science does not ask us to live at the edge of the observable universe. It asks us to understand that such an edge exists. When that understanding is in place, the familiar world gains context. The ground beneath your feet is not just ground. It is a fragment of a planet that formed from material created in earlier stars, orbiting a star in a galaxy shaped by invisible matter, moving through an expanding universe whose future is shaped by unseen energy. None of that needs to be actively contemplated for the ground to serve its purpose. But knowing it does something quiet to perspective. Safety in this sense is not ignorance, it is containment. A small view is what allows complexity to be lived rather than merely analysed. The idea that most of the universe is unreachable does not isolate us. It clarifies where we are connected. We are connected to what has reached us, to the light that arrived, to the matter that clumped here, to the conditions that allowed life to emerge on this particular planet at this particular time. That timing matters. We exist during an era when the universe is neither too young nor too old for observation. There are still distant galaxies visible. There are still traces of early conditions readable across the sky. There are still signals arriving that allow reconstruction of cosmic history. This is not guaranteed forever. Future observers, if they exist, may inherit a universe that appears much smaller. They may see fewer galaxies. They may have access to less information about cosmic origins. The small, safe view may shrink further, not because the universe changes in content, but because expansion changes access. That makes the present moment observationally rich, not in a dramatic sense, but in a factual one. We live at a time when the universe can still be studied deeply, even if never completely. Returning to the local does not mean dismissing the unknown. It means placing it appropriately. The unknown is not an empty threat looming beyond the horizon. It is a condition of reality. The universe does not present itself fully to any observer, anywhere. That includes hypothetical observers in other galaxies. They too would have horizons. They too would infer more than they observe. They too would be surrounded by darkness that means something is there, just not visible. This universality of limitation is quietly stabilizing. It means our perspective is not uniquely flawed. It is typical. From that angle, human knowledge looks less like a failed attempt at completeness, and more like a local adaptation. We know what we need to know to survive, to build, to ask questions, and to extend understanding outward as far as physics allows. The fact that understanding stops somewhere does not negate the journey to that point. There is also something important about returning without closure. The universe does not offer conclusions, it offers continuity. Expansion continues, structures evolve, questions remain open, knowledge accumulates without finishing. A small, safe view fits naturally within that ongoing process. It does not demand answers. It allows questions to remain part of the landscape. When you look up at the sky after absorbing the idea that most of the universe is unseen, the sky does not look emptier. It looks layered. Each point of light carries time. Each dark region carries mass. Each direction carries a horizon. But none of that needs to be resolved to rest under it. In everyday life, most of what matters happens at human scale. Conversations, decisions, attention, rest. The universe does not compete with these things. It contains them. Cosmic perspective does not replace personal perspective. It brackets it. There is also a subtle emotional adjustment that happens when the limits of observation are fully accepted. Anxiety often comes from the belief that something essential is missing and must be found. When the universe itself is known to be largely inaccessible, that pressure eases. Missing information is not a failure, it is expected. This does not diminish curiosity, it changes its tone. Curiosity becomes patient rather than urgent. Questions become companions rather than problems. The universe does not require us to solve it to exist meaningfully within it. Even the language of how little we have observed can sound negative if taken out of context, but the same statement can be reframed. We have observed enough to know that there is far more, enough to understand structure without exhausting it, enough to see patterns without claiming ownership. That balance matters. A small, safe view also protects against overstating conclusions. When you know that observation is limited, You become cautious about absolute claims. You distinguish between evidence and extrapolation. You become comfortable with provisional answers. This mindset is valuable beyond cosmology. It encourages intellectual humility in general. It resists extremes of certainty. It allows revision without collapse. From within this perspective, the universe is not a puzzle to be finished, but an environment to be interpreted gradually. Returning to Earth, quite literally, the scale contracts. Gravity feels steady. Time moves at a familiar pace. Objects behave predictably. These are not illusions. They are emergent properties of a universe that, despite its vastness and strangeness, allows stable local conditions. Those conditions are rare in cosmic terms, but common in lived experience. Both facts can be true at once. The small, safe view is where science connects back to life. Data becomes meaning only when it influences how we think, how we act, or how we rest. Knowledge that remains abstract and detached eventually loses relevance. Understanding the universe's limits does not pull us away from the present. It grounds us in it. You do not need to hold the entire universe in mind. No one can. What matters is knowing that what you see is not all there is, and that this is not a problem to solve, but a reality to acknowledge. From here, the sky can return to being simply the sky. The darkness does not demand interpretation. The stars do not require explanation. They can exist as part of the background of a world where attention slowly narrows back to breath, stillness, and familiarity. The universe continues doing what it does, expanding, evolving, carrying on beyond observation. And here, on this small rock, life continues as well, shaped by a tiny fraction of that vastness, yet entirely sufficient for the moment. Nothing needs to conclude. There is no final insight to arrive at. Understanding drifts, just as attention does, from the immense back to the immediate, carrying perspective without insisting on resolution. And in that drift, the knowledge that we see so little of the universe does not create distance. It creates space. Space to rest. Space to wonder quietly. Space to exist within a reality that is larger than comprehension, yet close enough to feel stable, familiar, and, for now, enough.